Hi everyone, and welcome to the Twilight Conference. I'm Iago González, and I will be your host for today and tomorrow. You can ask me wherever you want. I will be all the time in your service. We're here, some people in person, and there's some people seeing us through the streaming. I only want to say you all thank you for being here. The Twilight Conference comes from the twilight zone of the ocean. That place in the ocean where light starts to vanish, to disappear. That zone starts from 200 meters deep and goes through 1,000 meters deep. Our aim is to explore the twilight zone. So, for doing that, we have an amazing team of speakers. We have an amazing team of people here going to share their knowledge and give us a few insights on how we can get there. Only a few reminders for the people that you are in home seeing us from the streaming. Remember that you can do questions in any moment, all by YouTube and also by Twitch. We have a team that is and they're going to go through them. For people that are here, first of all, remember that you have coffee outside in the hall, coffee in the hall. Second, remind that you can be here or be outside, but please do not move during the presentations, okay? Third, we're going to have always a chair and a team of speakers. The chair will manage the questions. 4, thank you very much for 4 special organizations that help us being here. My name is Iago, and as I told you before, I'm part of Monodon team, but Monodon didn't build this alone. First, I want to say thank you to the team of SAES, a company of electronic underwater technology. Second, I want to say thank you to the INTA CEIPAR. The place where we are the INTA CEIPAR facilities. Third, I want to say thank you to the John Academy of Spain. And 4, I want to say thank you to Navantia, the public company specialized in building ships in Spain. Navantia has a huge, more than 400 years old tradition on building ships and working with scientists all around the world. But now we're in a different moment. So I want to call someone really special for me, Tamara Codón, Head of Development of Navantia. Please.
Thank you, Iago. For me, it's a pleasure to be called to be here to open this event because I consider it's a great milestone for Navantia. We are going through transformation and cultural evolution, and we really support talent in our company. So when Patricia, the head of Monodon, called me and told me about this great event, I was so excited because it's a great opportunity for us to open to the world and also to learn from all of you. I want to join Iago in this welcoming that he has said because we appreciate a lot that you have moved from Japan, from USA, from around Europe, Spain, and you are here sharing with us. I hope that you spent great days and you learn a lot. Thank you very much.
Okay. Thank you very much. So, we're not going to lose more time. We're not going to dedicate more time to this. We're going to call Cecilia, please, to the stage. Cecilia is the Vice Dean of Research and Scientific Works in the Universidad Politécnica de Madrid. And she is one of our greatest collaborators. Cecilia, the stage is yours.
Okay, thank you. Thank you so much. Good morning, everyone. I'm here to introduce our first roundtable, and I want to say something about underwater robotics. Underwater robots has become an essential tool for exploring, monitoring, and maintaining both the ocean environment and the infrastructures that humans have built within it. Given that the Earth ocean covers over 70% of the planet's surface and remain largely uncharted, this robot plays a crucial role in unlocking the mysteries of the deep sea and tackling the complex challenges related to the ocean conservation, resource management, environmental protection, and the security and defense of our infrastructures and borders. The harsh condition of deep ocean, such as extreme pressure, temperature, and low gravity, make human exploration difficult and hazardous. Underwater robots, however, are capable of reaching depths that are inaccessible for humans, enable scientists to study marine ecosystems, biodiversity, and geological features that would otherwise remain out of the reach. Today, in this roundtable, we have the privilege of learning from leader global experts about the latest advancement in underwater robotics and cutting-edge technologies that are driving the success of underwater mission. Professor Joao Sousa, Professor Pablo Otero, Professor Shinya Aoi, thank you so much for attending to this conference, and you are very welcome. Now, we will ask our two first speakers, Professor Joao Sousa and Professor Pablo Otero, to come up to the stage, please. It's an honor for me to introduce Professor Joao Sousa, our first speaker. Professor, you can sit.
Okay.
I will be in the center, please. So, yes, perfect. Thank you so much. So, Professor Joao Sousa is professor at the Electrical and Computer Engineer Department from Porto University in Portugal. He has his PhD and master in electrical engineer, both of which were awarded by the University of Porto. His research interests include autonomous underwater, surface and air vehicles, planning and execution control for networked vehicle systems, optimization and control, cyber physical systems, and application of networked vehicle systems to the ocean science, security, and defense. In the past 35 years, he has involved in several projects, several technical committees, and also that include the NATO committees and also Sweden Marine Robotics Center. So Professor Joao Sousa, you are welcome, and you can come in for your presentation.
Thank you very much. Good morning, buenos dias. First of all, I would like to say it's a pleasure and an honor to be here. I'm really happy with this kind invitation. And so now I'll talk about future operations with multi-domain maritime unmanned systems. And I'll discuss the systems of systems perspective. And so this is the outline of my presentation. So I'll start with an overview of what we do at Porto University, then an aside on complex systems and control architectures. Then I'll go into operations with multiple UXVs. And this will provide the background to discuss some recent trends and where are we going next. And this is the reason why we are here, the blue planet. This was alluded to before, but this is beautiful, but it's a bit misleading. And the naked reality is that there's not much water in the planet. So this sphere represents all of Earth's water, and as you can tell, it's not big, and the small one represents fresh water. So, and there's an important observation by Walter Munk in regards to oceanography, but the ocean is still undersampled for several reasons, and this is one of the reasons. So if you look at observation footprints for different assets or technologies, if you will, in X you have distance, and in Y you have time. And then if you look, for example, for AUVs, they have kind of a small footprint in terms of observation. Then if you look at floaters and drifters, a kind of different footprint. But the important observation is that if you really want to observe something in those scales, you can see this a kind of a sort of a circle here, distorted circle. It tells you that to do the right thing, you need multiple assets to achieve some decent observations. Now I'll switch to what we are doing in our lab at Porto University. So we've been designing, building, deploying autonomous underwater surface and their vehicles for networked operations. Applications include ocean sciences, security and defense. And we've also been developing the software that enables all of these systems to work together as a system. So, and this is our vision for a sustained presence in the ocean. Definitely you'll need multiple assets, but probably more important than these multiple assets are multiple interactions. So interoperated communication links, sensing links, mixed initiative interactions, meaning operators in or on the planning and control loops. Vehicles will come and go, same thing with the operators. There's also the issue of scalability. Now we know how to handle, let's say, 10, 15 vehicles at a time. What about 100? What about 1,000? We are not there yet. We've also been using vehicles as data mules when you don't have permanent connectivity. There's also the issue, even more and more, about distributed computations. Then using some terminology from computer science, you can talk about physical mobile locality, which basically means that you can talk about launch and recovery by other assets. But in our view, we want to treat this ensemble of assets as a system that has properties that are a function of the vehicles, a function of the communication networks, and a function of the interactions that you establish over these. So we want the system to have organization-like properties. So we want to issue high-level directives, commands, objectives, doesn't matter, such as go and find this, or sample this area, or find the source of this plume, and then it will be up to the vehicles to organize themselves to achieve that goal. Of course, you can say this is PowerPoint engineering, granted, but we are developing the tools and technologies to achieve this vision. So in our lab, we have lots of different assets and also lots of different units. We've been mainly designing, building, and deploying most of them. We have some exotic ones. For example, this one in the bottom left, it's an octocopter that can take off and land from water, and it's what we call a flying modem. We also have Autonaut. This was not built by us, but all the computer systems and electronics are ours, and this can cross the Atlantic. And the important thing is that most of these vehicles share the same software infrastructure and some of the computational infrastructure. Moreover, these are interoperable, meaning that they can talk to each other. So we have different types of assets. LAUVs, this is an old one. Then USVs, UAVs, and then again the flying modem. For the AUVs, you just need to make sure that there's water when you throw it in the water. It happened before that people were not that careful. Something that is very important for us is the software behind all of these vehicles. So that's what we call our software toolchain. So we have Dune running on board. You have IMC, which is our protocol for communications. So all of our assets and control stations talk IMC. Then you have Neptus for planning and execution control that runs on your laptop. And then you have Ripples. It's a more recent development, which basically exposes all of these on the internet. So, and then we have different assets powered by our software toolchain. And then we also have other support for other interoperability frameworks, for example, Cattle. And Cattle plus Ripples, then we have a web-enabled control center. You can see it here in operation on a ship. So we also have onboard deliberation. So, for example, we have T-Rex running on our vehicles. And without going into details, what you can say that we have is, so T-Rex is running on our vehicles, then it receives high-level objectives, and then new plans are generated on board when new objectives are received or when there's an error executing some objective. But we went one step further, which is, in addition to have multiple assets running T-Rex, we also had another planner called Eroptus running on a ship that was generating coordinated objectives and that were sent to these guys for execution. Ripples, just a kind of a brief overview. So it's a multi-vehicle planning execution control, 24/7. So it has supports for multiple maps, interoperability standards, multi-domain communications. For example, from Ripples, we can basically talk with a submerged submarine. We also have user access control. We support hierarchical C2 architectures. We ingest data from multiple sources. We have configurable alerts, multiple visualization layers, and this gives you a flavor for some of these visualization layers from Ripples. And we have a spin-off, Ocean Scan. So they commercialized the light AUV. I think for the moment there are over 100 of those in operation all over the world. And recently we were funded to start the Center for Aquatic Operations, so we are going for aquatic operations. The model is basically the same, so multiple assets, long endurance, and we also want our partners to be able to access our infrastructure and run these operations. Of course, we are, let's say, our pool of assets is increasing. And these are some of our operation areas. So we still need to go to Antarctica. Next year, hopefully we will be there. And now an aside on control architectures. Why? Because this relates to this notion of systems. So let's think about a completely different problem, which is, for example, how to maximize throughput in highways. So and the question here is how to decompose a complex problem into manageable subproblems. And this was a while back when Praveen Varaya at UC Berkeley came up with this idea, okay, why don't we come up with platoons? And if a platoon is running at something like 60 miles per hour with spacing between cars in the order of 2 meters, then not only can pack more cars per kilometer, but if they all travel at the same speed, you also increase throughput. Now think about the whole highway and how do you go about that. And he came up with this hierarchical control architecture. This was a while back, but it's still quite relevant. So you have vehicle dynamics, so basically accelerator, brakes, whatever. Then you have regulation, which takes care of maneuvers, joint platoon, switch lanes, this and that. On top of that, you have a coordination layer, which takes care of motion coordination among several vehicles. And then you have the link layer. The highway has links between junctions. And then what is set here is a nominal speed for that link that all the platoons should follow. And then on top of that, you have a network layer that takes control of traffic distribution. And so you see here a very complex problem was partitioned into manageable subproblems using different models. Different problem, and actually here we use exactly the same technologies. So mobile offshore base, without going into, this was a feasibility study. The idea was to align several modules under DP and then being able to extend flexible bridges among them, or between them. So then again, a layered control architecture. Another one, which is a bit more crazy, mixed initiative control of automated teams, in which we were given complex task, and then we were given threat models, and then we were supposed to go and remove some stuff from the map. And then again, we came up with a hierarchy of planning and execution control without going into details. So we started with primary targets, then you would select secondary targets, and then you had target sequencing and paths, tasks and subtasks, team allocations and deadlines, and then execution control. So this is to say that planning and execution control of large-scale systems is really important for what we want to do in the future. And there are several principles aimed at establishing a scientific framework for analysis and design. So the principle of self-containment, the principle of coherence, and other principles. Curiously, this is quite recent. There is this paper by John Doyle, one of the big names in controls. It came out recently towards a theory of control architecture. So I would like to revisit this soon. Now let's briefly talk about operation with multiple UXVs. By UXVs, I mean UUVs, USVs, and UAVs. So, and I'll talk about stuff that we did in the past, in which we had systems with evolving complexity, but no higher layer, higher level of organization abstractions. Let's be a bit more concrete about this. So we've been, I co-founded, and we've been co-organizing the REP-MUS exercise that you see here. So it's being jointly organized by us, by the Portuguese Navy, by NATO, CMRE, and also EDA. It's a large-scale exercise. It's about operational experimentation and about evaluation and testing in operational scenarios. And then this is developed in the triple helix framework. So you have academia, industry, and the armed forces all working together. And there are several focus areas. And these are some of the assets that we use in this exercise. This has been growing a lot. So, for example, into 2024, this took place in September. This is an annual exercise that started in 2010. We had 23 participating countries and 7 observer countries. And I don't have the exact figures for 2023 and 2024, but just to give you a sense for size, so in September, we had over 62 UUVs operating in Sesimbra, in Portugal, under this exercise. One of the focus areas is interconnectivity, which has to do with the interoperability, and also interchangeability, being able to hand over assets between control centers. We have a very complex, and this is also very important, we have a very complex task organization structure. This is basically the human side of it, quite complex, because keep in mind that we had lots of assets here. So not only manned assets, but also manned vessels. For example, we had 18 ships involved in this exercise. Now, this is our perspective about eye-to-eye interoperability into interchangeability. So this is our view from Porto University. So we have some of our assets, like the LAUVs and Manta gateways that can talk with Neptus, now going back to software, and can also send information directly using SATCOMs to ripples to the cloud, which basically also services a control center. And this control center also ingests data coming through different networks to ripples, and this data is broadcasted by all of the other assets. So basically, we can see what is going on in this region, and we can also retask vehicles. So this is really large scale. A few simple examples of what we've done over the years. This is just Porto University and some of our partners. For example, having a control station exchanging commands and data with a submerged UUV, using first a UAV, then a wave glider with a communications gateway. It worked pretty well. Then we've also been playing with manned submarines, and we did several different things. So we tested acoustic communications between Arpão, which is one of our submarines, and the LUV for situation awareness, but also for being able to task the LUV from Arpão. We also had diver-assisted launch and recovery of LUV from Arpão, and we also participated in this distress signal response exercise. Then again, now talking about some complex operations. So imagine that you have surface and UUVs, and you have onboard and offboard software, and you have mission specifications for a group of heterogeneous vehicles. You have systems-level planning and execution control with minimal human intervention, one operator, and then you have interfaces for heterogeneous vehicles. And this gives you flavor for what was done there, a compressed flavor, of course. So multiple assets, and then this is the perspective from Neptus. So to the right, you can see these boxes that these allude to different vehicles, and then again, you can specify, hey, I want you guys to map this area. Then the area is split into several sub-areas, and then these guys are supposed to map these areas, and if there's a problem between them, they reach some agreement using acoustic communications to redistribute tasks. Another example, somewhat complex, about interoperability. So we had some of our AUVs underwater. There were some AUVs from the Undersea Warfare Center, Newport, Rhode Island. There was a seabed node with acoustic modems. There was a WAMV, a surface vessel, with communications gateway, so enabling underwater and above water communications. Then we had our flying modem, and the operator could send commands and mission plans to the flying modem that then could land close to the seabed node and send data and commands to the seabed node. And same thing could be done with the help of the USV and the AUVs. But the thing is, once data or mission plans were available in the seabed node, then UUVs could go by the seabed node and extract mission plans. Something that we did this year, this was the first attempt in this direction, was counter UXVs. This year was just about the detection. So we had several USVs towing acoustic arrays. We also had vector acoustic sensors mounted on buoys. The idea was to be able to detect other UUVs operating in the area. And then this data was fed to a command center. In this command center, we had a sort of a synthetic model of what was going on there. And then based on that, we were able to retask the USVs to basically maximize probability of detection. Something else that we did, then again, quite relevant, was this cruise in the Pacific. I had a big team. This is part of my team. This took place on board the RV Falcor. So we had people from Spain, from Portugal, US, and Norway. We also had support from NASA, Ames, and SINTEF. And this was the main goal of the cruise, to demonstrate a novel multi-vehicle system capable of finding, tracking, and sampling features of the ocean with adaptive spatial and temporal resolution. So I have a short video here. There is some sound, but if there's no sound, okay, perfect, thank you.
During this expedition, our team has created a system to conduct oceanographic surveys with unprecedented levels of detail and scale. Approximately 1,000 miles off the coast of Southern California, we are studying the subtropical front. Here,
two masses of water collide, which generate a unique mix of physical, chemical, and biological features. Before the expedition, autonomous vessels helped us determine the approximate location of the front. When we arrived here, we deployed CTDs to gain a more precise understanding of its spatial dynamics. Our autonomous underwater vehicles, which were specifically designed for this expedition, can cover hundreds of kilometers and stay in the water for up to 50 hours. They travel in a yo-yo pattern, sending real-time data back to the ship every time they surface. Our fixed-wing vertical takeoff UAVs can fly faster and further than quadcopters and carry a variety of sensors. The data our autonomous vehicles collect helps us locate biological hotspots where we conduct more detailed sampling.
We are deploying very advanced technology that needs to be refined through experimentation. And by doing that, we hope to establish some of the foundations for the future of oceanographic survey. Okay, so we had a complex ocean observation system based on the Falcor. So we deployed 7 UUVs from the Falcor. We had the support of 1 wave glider and 2 sail drones, USVs. Then for communications, we were using SATCOMs, and then we're kind of handling all of this data with the help of ripples. So we had a control center on board the Falcor and another one in Portugal. This is exactly what you had. So we were operating 24/7 for about 2 weeks, and so different views. This was a view from the Falcor in the control center, and some 3D view of the front, which was very exciting. We saw some very interesting things.
So we take all these different systems that go beyond the footprint of what a ship can do. They can be 20 miles this way, 20 miles that way, and help us understand the oceans a lot better than we do now.
So the important thing here is that we had a huge operational footprint. So our op area was in the order of 40 nautical miles by 50 nautical miles, always having vehicles in the water to observe what was going on there. Next year, we'll run this experiment. So we'll have one of our USVs crossing, hopefully. You never know with the ocean, as you know probably much better than me. So we'll have one of our USVs crossing from continental Portugal to the Azores, and along the way, so there will be some deviations from the optimal path to maximize the scientific return. Now, I would like just to say a few words. Of course, this is not a thorough discussion of recent trends, but just a few words. The first one is this observation by Ray Kurzweil from 2001, which says that technological change is exponential, and returns such as chip speed and cost effectiveness also increase exponentially. And actually, if you look at some market trends, yeah, this kind of seems right, but there's a problem which is captured under what people call the Martek's law, which basically states that technology changes exponentially fast, but organizations change logarithmically slow, meaning that this gap increases with time. And so this eventually will require a reset of the organizations, and this reset can be quite radical. From our perspective, we need, and now looking back at what we did in the past, we need new abstractions, vehicle capabilities, composition, in some sense to be defined, teams, inter-team coordination, different organization structures, and we need to go back to the scientific method with operational experimentation. So develop your concepts, ideas, you test them, then you go about operational experimentation, and then you come back to the drawing board if there's a need to. Autonomy, yes, lots of people are talking about autonomy. We are all in favor of autonomy. Our friends, for example, from Girona, we are all in favor of this, but still there's a, what about number of operators per vehicle? 0? Not necessary. So this came out recently, for example, self-driving cars and so-called robo-taxis. And for example, one of the companies has, on average, 1.5 operators per vehicle. So we are not there yet, and in the REP-MUS, we even had more operators per vehicle. Another idea, and so I was part of the Innovation Advisory Board to the MUS initiative from NATO, and we came up with this idea, the digital ocean, that was then again submitted by NATO, and it was approved by NATO, and they started this initiative this year. There was the first Digital Ocean Conference, and this provides a kind of motivation for future
NATO's vision of a digital ocean will be implemented through the creation of a vast, global-scale network of sensors, from seabed through the ocean's surface to space, across millions of miles. It includes unmanned surface vessels, subsea sensors, satellites, ships, buoys, and drones. It builds on the assets we already have and creates an interconnected mesh of immediate data and communication fused together with AI algorithms, computer vision, and acoustic analysis technologies powered by machine learning, all coming together to create a multinational advanced ocean management platform, the digital ocean. A digital ocean will help us mitigate the risks of climate change, protect undersea critical infrastructure, and safeguard essential supply chains and strategic waterways. It will help us counter piracy, illegal fishing, and trafficking. Because ultimately, we need to see our oceans to protect them. A digital ocean will help us do that more affordably, sustainably, and safely.
Okay, so this kind of presents a challenge for the future, and this is why I would like to discuss where are we going next, at least from our perspective, and I think it's not only from our perspective. First of all, we need to be a bit more ambitious in the sense of the type of systems that we are dealing with. So we want to have systems of systems endowed with dynamic layered organization structures, and keep in mind that for the moment, people only talk about vehicles, but we need vehicles with different organization structures that incorporate teams, inter-team coordination, creation and deletion of teams, load balancing between teams, and with operators on the loop and not in the loop. Then again, going back to our first comments, or one of our first comments, we want to have a system that has properties that are a function of the assets, a function of the communication networks, and a function of the interactions that you establish over these. Of course, it's difficult to make predictions, especially about the future, but we try. Now, kind of some observations. First of all, how to cope with scale and complexity. And as you can tell, I'm going towards control architectures. First of all, terminology is confusing and hence dangerous. And semantic overload is even worse. For example, people have been talking a lot about swarming. Nothing against swarming. We've also done that. But we need to go beyond that. And so, but then again, who am I to say that? So Marco Dorigo, so he came up with this paper, Reflections on Future of Swarms. This came up in Science Robotics something like 2 years ago. While swarm robotics takes inspiration from self-organization systems, future robotic swarms should include hierarchical forms of control beyond self-organization to deal with the assignment of larger responsibilities, task allocation, creation of task-oriented teams, and coordination of specific activities. And then again, I think that you all agree that this is not a swarm. So we need more advanced concepts. And how shall we go about that? Let's first discuss vehicles. Vehicles have some, let's say, can be organized into platforms, payload, mechanical interfaces, communication, command and control, software, and computation. But the observation is that most COTS vehicles are not designed for interactions, period. Then you have some technical features, and then imagine that you buy a UUV from this vendor, a USV from another vendor, a UAV from some other vendor, and you also have some hybrid vehicle. But the important thing is that if these guys are not compatible up to a certain extent in terms of communications, in terms of interoperability, in terms of cooperation skills, what can I do that can be of use to other guys? There's not much you can do with them as a team. You can operate those as single entities, but not as a team. On the other hand, if you look at this matrix of capabilities, and if these guys are somewhat compatible, then you can operate those in such a way that you can get out of a team notion to be defined. You can get some team capabilities that were not there before. They were not there in each individual vehicles. And this is an important observation for teams. And now you can be a bit more ambitious, and this is pretty much my last slide. Then you can go into systems of systems, but being quite ambitious here. So you can have vehicles, then you can organize those into teams. Teams, in turn, can have sub-teams. Then you can also have control stations with operators, different control centers, handover of command and control between these centers. And then, for example, some teams can have different properties. Team A is not allowed, this is what this continuous red line represents, is not allowed to interact with other assets outside. Same thing with TB, but these are allowed to exchange assets between them. Now, if you look at Team C, here there's a team lead, then you have different sub-teams, and each of these teams or each of these sub-teams have different control strategies. Some of them could be leader-follower, and others could be, for example, pretty much decentralized. If you go for a leader-follower, you can use, then again, you can go into game theory, and there are some recent developments in game theory and machine learning, which seem quite interesting. And the interesting abstraction here are Stackelberg games. But then again, Team C is allowed to interact with other external assets. Of course, this is, I'm almost there. This is quite complex. We are working on this. As you can get, now we have the motivation to get here. We have the tools and technologies that will enable to get here. But still, we need more developments. So our research is at the intersection of control and computation. We need lots of different concepts from computation. So we have different types of mobilities, physical and computational, and even in computational mobility, there are different types. I won't go into details. Software and hardware, you need dynamic reconfiguration, you need dynamic access control, you need task composition and decomposition, we need hierarchical level fault identification and recovery, and then you need also new notions of behavior equivalence and satisfaction. And this is pretty much what I had to say, so thank you very much.
Thank you so much, Professor Joao. Questions? I have a lot of questions, but I prefer that people here. No questions? Okay, go ahead, please. I don't know. Maybe yes. Yes, you should. Yes. The mic is coming. Yeah.
Hi, Joao. Thank you very much for this very nice presentation. In this hierarchy that you were presenting on assets and sub-teams and teams and all this hierarchy, how do you imagine the communication with the human at the end, with all these resources that are available? And I think one of the challenging things also will be to how to transmit or have a dashboard in which the human is able to tell all this infrastructure what is the aim of what type of questions he wants to find out or discover or measure in the ocean?
Thank you very much. This is a great question. And this is also one of the reasons why we need hierarchies to basically kind of put limits on what we need to exchange to achieve some level of coordination. And for example, in this kind of a micro project, which was about suppression of enemy air defenses, was a bad application, but still very interesting from mathematical point of view. We realized that after a while, if you do it right in terms of organization, and to understand what is going on, you just need to monitor a few variables at each layer. So just by looking at a few variables at each layer, you can understand, hey, the state of the system is this right now, and because this is happening or so, probably the next state will be this one. And then you go up in the hierarchy. So first of all, you have the notion of, okay, how is the sub-team doing? How is the team doing? How is, then again, how are teams doing in terms of executing the mission that was assigned to them? And this is quite relevant to us, as you know much better than me, which is you also need to exchange data. And acoustic communications is not exactly the best way to exchange data. So this should also be incorporated in the control architecture design so that you make sure that, hey, if you need high bandwidth, then you should have assets that could take care of that to basically make sure that you get some data every now and then, let's say through some high bandwidth kind of means of communication. So, but it's still a very tough question. So, as you know, I'm looking forward to your presentation by, let's say, getting lots of data from, let's say, video or so. Yeah.
Thank you.
Thank you.
Another question? I have one for you. It's related to the awareness of the underwater system. How do you, in terms of cooperative multi-agent system, I realize that your underwater robots are homogeneous, or I mean that all of them have the same capabilities, or?
No.
No?
Not exactly.
Not exactly?
Yeah.
And they know what happened to their partners? I mean, what is the level of awareness that you have underwater in the underwater environment?
Okay, yeah, which is a related question. So then again, it boils down to communications, but also something else, which is cooperation skills. So in some of these experiments, so when a vehicle joins a network, it announces. Then again, the meaning of announcement is, there's a question mark here, but let's kind of take this abstraction. Announces its capabilities, so that the other guys in control centers know their capabilities, so that when start interacting, they know, hey, this guy has a very nice side-scan sonar or a nice video camera. This guy is quite poor in terms of navigation skills, but if there's another vehicle that is quite good in terms of navigation, then probably this guy can help the other one in terms of navigation. So the first step is broadcasting or announcing their capabilities. And second one is making sure that you receive those so that you can take decisions. Of course, by receiving those, it doesn't mean that you receive those in real time. There could be some delays, and this should also be accounted for in the control architecture.
Thank you so much.
Thank you.
We are going to the next speaker, so thank you so much, Professor Joao, for your talk.
Thank you.
So now we are going with Professor Pablo Otero. He's associated professor from University of Malaga in Malaga, Spain. His PhD in telecommunications from Communication Engineering School. His research interests include antennas, transducers, and underwater communication. In the last 25 years, he was involved in several projects about communications and radar systems, worked with corporations like Standard Electrica, Navantia, Telefonica, and several universities such as École Polytechnique Fédérale of Lausanne, University of Sevilla, and University of Malaga as well. Professor Pablo Otero, you're welcome, please.
Good morning, everybody. The first thing I want to say is I'm very grateful to Navantia Monodon for inviting me. Thank you very much. It's an important opportunity to show our work. As Tamara said, well,
This one. This one.
Ah, okay.
This one.
Excuse me. Excuse me.
No problem.
Thank you. These are the contents of my presentation. I will, first of all, present my institution, and then I will go into the main subject of my talk. Please allow me to do this. I come from the University of Malaga. Malaga is an important city in Spain. It can be 4th to 6th. That depends on how you count or how you measure importance. This is in the Mediterranean coast of Spain. You can see it there for people who don't know. No, it's okay. It's okay. You know, sometimes the mechanical things are better, you know. This is Malaga, in the Mediterranean coast. Excuse me. It's okay, excuse me. You know? The University of Malaga is a medium to large size university in Spain. We have over 38,000 students. We have a huge offer of different subjects, and we have, well, common infrastructure of other universities. And this is my school, the Telecommunication Engineering School. Well, this is not my team. This is just a picture that I took, not me because I'm on the picture, that we took one day after an international meeting, but I wanted you to see the entrance. And we offer the 3 common levels of university studies. We have a bachelor's curriculum with 5 majors, 4 master's curricula, one leading to become a professional engineer. And also we have a doctoral program, but doctoral programs are centralized by the doctoral school, which is a virtual faculty of the university. Okay. I'm the head of the Institute of Oceanic Engineering Research. In Spain, university institutes have 3 functions. They are research, of course, but also transfer. Research results transfer to industry, and also training. From the institute, not from the school, we teach courses on masters and doctoral graduate courses. Okay. This is the institute. It is a young institute. It started in 2019, and we gathered all the engineering activities at the University of Malaga that were involved with oceans and the seas. And we are 5 groups inside the institute. One is works in materials. We have 2 scientist groups, algebra and oceanography, and we have the strongest part of the group is signals and communications and microelectronics. And we work together with 2 groups from the University of Cádiz, but from the administrative point of view, they are not members of the institute, but is the Naval Engineering School of the University of Cádiz and the Coastal Engineering Department also. Now, let's go to the main point of my talk, underwater communications. I had prepared this slide, but I think the best presentation has been done by Professor Sousa, explaining why communications are needed. You know. All of you can easily understand. All of you, or all of us, we have a device like this one in our pocket. This is a computer with incredible and awesome computation capacity that we couldn't imagine 20 years ago. But if you remove the communications capability of this device, this is almost nothing. No, it's like a ship without a propeller. No, for you, most of you are naval engineers. This one, I think, it was published. This was when the Nord Stream attack, you know, and that one is a picture of the deployment of an underwater submarine cable. And there is a journalist in Spain who is an expert in geopolitics, is Mr. Enrique Juliana, who 2 or 3 months ago, he's mentioned in his article that what would happen if one communication cable was cut in the sea, and that can be really, really bad for our way of life. And that happened. Last Sunday, on the Spanish newspapers, we read that a communication cable from Germany to Denmark, and vice versa, of course, was cut. They said it was an accident, but who knows? They don't know. At least we don't know enough information about that. This is a very naive slide, but I think it presents very well the scenario of the communications, of the underwater communication. We have drones, we have maybe onshore infrastructures that cannot be only gas pipes or oil pipes, that can be also mining. And we have the need to communicate all those vehicles among them, and also with the external world. This is where we have to work. Okay. When we talk about underwater communication, we say, of course, wireless. We are not thinking on drones with a cable. You know very well the main 2 problems underwater is there is nowhere to breathe, and there is no electrical outlet to plug our devices. What are the options? What are the options to have underwater communications? We consider 3 options: radio frequency, like our phones, optical, and acoustic waves. RF, electromagnetic propagation in the salted water is very short. The range, we are talking about centimeters, maybe a few meters, depending on the frequency. That makes no sense to communicate drones. Okay, and the optical, maybe the range is larger, but the problem is aiming the beam of the optical devices. So we went to acoustic waves. Well, not me, but maybe researchers before me, and that is what we are doing. What is the situation for underwater acoustics? The aim of my talk was what can we expect from underwater communication, and why? This is when I was invited, I say, what can be of interest for people who are not telecommunication engineers? And I thought, okay, what I can tell them is what they can expect from communications, and if possible, why, because knowing why helps you to solve the problems. Okay, this is the situation. We have computers with capacities is incredible, but in between the channel is like a path in the mountains. It's like trying to drive a Ferrari. We have the Ferrari, we have an F1 vehicle, but we have to go through a very hostile, harsh path. Okay, so what we need is a good four-wheel drive and very robust. And the reason, as I tell you, is the channel. The acoustic channel is the worst channel we can imagine. Bandwidth very narrow, attenuation very high, noise very high, multipath and fading unbearable. We cannot take that, and it is time variant, which is well, for communication people, this is a very bad thing to have a variant channel. Now imagine that you are driving a car and suddenly the turn, instead of being on the right, is on the left, and you didn't expect it. What changes with time? Propagation velocity with time and space, and that results in a very high dispersion. Dispersion is not easy, as a concept is not easy to explain, but the results of dispersion is that it distorts the information that you are trying to bring from a transmitter to a receiver. So the net capacity of the channel is very low, and this, when you are trying to do drones on big systems, you need to be aware of that, okay? So what we are doing about that? Okay, I'm going to go through those characteristics. This is attenuation to give an idea of figures. If we go here to 10 dBs per kilometer, these are dBs per kilometer, it's a 10 kilohertz. At 10 kilohertz, if we send a signal at 10 kilohertz, 1 kilometer far, we have lost 90% of the power just because of water absorption. In wave propagation, there are other attenuations, but just in water absorption, we have lost 90% of the power. That is the reason of the very low, one of the reasons of the very low bandwidth, okay? Excuse me. We developed several propagation models to analyze what is going on, and we realized that a second big problem is multipath. Multipath is energy arriving to the receiver from through different paths. Okay, you can see this is the effect of multipath. There are regions where you don't receive anything. There are regions where you receive a lot of or even a little bit more power than if it was in open space. No? And on the left side, these are the results that shows fading. Fading is suddenly you don't receive almost any power on your receiver, and that makes that the communication is interrupted. And that changes very, very quickly. You see, you are moving in distance, and you are moving, and you are receiving, and suddenly you don't receive. Okay. Noise. We have so many. We think that what is underwater that can generate noise, but there are many things there that can generate noise. You have a picture there. We have submarines. I mean engines, propellers. We have marine life. We have human activity. We have the sound of ships, and you know much better than I do. The ships traffic in the world is increasing and increasing and increasing. We have every time we have more ship noise in the sea. Okay, and we have also bubbles. We have surface waves or the wind on the surface of the sea. A lot of noise. Dispersion. This is what I told you that the result of dispersion is that the signal at the receiver is distorted, so maybe you cannot recognize what is like if you are speaking and suddenly something distorts what you are hearing and you cannot understand what the speaker is saying. There is a key. We have two problems here. Multipath. Multipath is, as I said, energy coming from different paths or through different paths and moving scatterers. Multipath, what it does is, there is a key point there. You see, I put it in red. The propagation velocity of sound in the sea is very, very low compared to electromagnetics in air. It's around 1,500 meters per second. So that makes that the propagation time, the time that needs a signal to go from the transmitter to the receiver, it is comparable to the transmission time. And the result of this is that capacity is still lower. Capacity in terms of information that it can travel through the channel. Okay. But not only that, is that in terms of multipath, if I imagine that you are transmitting 1 bit, you know, 1 bit is like 1 impulse. You receive that impulse, okay, but you receive a copy of that impulse because of multipath. And due to that very small speed, that can be almost 10%. This is an example but with realistic figures. That can be 10% of the duration of the bit. That makes a big problem to detect it or to recognize what it is. And the second problem is what we call Doppler spread. The frequency where the information is modulated will spread over the frequency axis. And the reason is, again, that very small c. Okay, compare. So this term that changes the transmitted frequency to the received frequency, that term that in electromagnetics, here, is around 10 to the minus 8, in acoustic is 5 orders of magnitude bigger. And that makes, again, very difficult to receive, to detect the information that you receive. Okay. Well, I think I put too many slides. What is the knowledge then about propagation? I think physical models, they are very interesting. We can publish articles in the technical journals, but they are not useful for planning underwater links. So finally, we go to statistics. And we still have very few statistics about sound propagation or ultrasonic propagation underwater. Okay, maybe the big countries, their defense forces, they have those knowledge, but in the literature we have very few. I think we still need to work on that. Networks. I will talk about networks a little bit later. Regulation. There is no legal regulation about underwater communication similar to what we have in electromagnetics. In electromagnetics, we have the International Telecommunication Unit. They fix rules for the different countries to use the radio frequency spectrum. That is not true underwater, or not yet. Okay? But we have a couple of standards, and they are NATO standards. The first one is ANEP, ANEP 85. It deals with analog communications, and its purpose was emergency in submarines. Okay, but now talking about what we are talking today, we have the second standard that is called JANUS, and is standard ANEP 87, and the version 2. It was published in February this same year. Okay, and this, I want to mention here that this standard uses a transmission technique that we call frequency hopped binary frequency shift gain. Is FHBFSK. Okay, and the reason of using this is a very simple, in terms of communication, this is a very simple transmission modulation. And the reason that they wrote, this is literal from the standard, is its robustness in the harsh underwater acoustic propagation environment and simplicity of implementation. I think this is important. And a second sentence that was that is in the standard is, it is used in at least 2 leading commercial product modems. So there are at least 2 companies who already have those devices in their catalog. Okay. We have explored, I think, all transmission techniques, very sophisticated transmission techniques that had been used in radio frequency have been explored for the underwater. And the conclusion, I think all the experts that I talked with, they mentioned the same thing. Let's go for a robust and simple thing, because anyway the channel is so bad that what to do. This is the last line. The common feeling is that a simple and robust modulation performs better in the harsh environment. Okay. Transceivers. What are the transceivers in underwater communications? Have 2 parts: the electronics and the transducer. Okay. This is a picture of the electronics in OEM configuration that can be integrated with other electronics. There on the left, it is encapsulated in the cylinder. And then the hydrophone, this is the second part, this hydrophone, or that one on the left part of the cylinder. That is the hydrophone. The hydrophone plays the same role that an antenna in electromagnetic communications. It is, but there is a difference. It is a transducer that changes the nature of energy from electric to acoustic. Okay, and normally they are done. They use the piezoelectric effect, And the main problem with those things is that they are very, very difficult to do impedance matching. Okay, that is an electrical concept. Maybe it's not, this is not the place. The good thing is that antenna theory, developed in the 40s, in the 50s of the last century, can be directly applicable to arrays of hydrophones to obtain the beams almost with different patterns. Okay. What is available in the market? There are several companies. I listed, I wrote there several of them. They are written in the alphabetical order. I have no interest in any of them. I'm just a modest university professor. But you have Evologics, Convert, LinkWest, very, very renowned companies that already have off-the-shelf products that you can use and integrate in your systems. Typical carrier frequency. That doesn't mean that the figures, the real figures, will be there. Maybe they are outside those ranges, but this is typical. Carrier frequencies, you see, 10 kilohertz to 60 kilohertz. There is not much bandwidth there. Range, 1,000, 6,000 meters. We have to pay attention to something. Sometimes there is a company that says, I have a modem that with a range of 6,000 meters, and it has a bit rate of 10 kilobits per second. Yes, it is true, but when it works at 10 kilobit per second, the range is only 1,000 meters, not 6,000 meters. There is a trade-off between power, consumption, that means autonomy, and remember, we don't have plugs down there, and range and bit rate. Okay. You can increase one, but then you decrease the other two. Okay. Networks, this is very important, and I think Professor Sousa explained it very well. When you have different drones moving around and they need to communicate one each other. Ranges are so short that we need to talk about relay communications. I mean, you cannot, with a range of 2,000 meters, you cannot reach where you want to reach. So we need to do relay-based topologies, network topologies. If the nodes are fixed, this is easier. In that case, the best technique is TDMA, time division multiple access, because this is the optimal use of the spectrum. Okay, but when they are moving, that changes, and we need a communication strategy, and the topology will be dynamic. And the problem, what happens with this is that handshake between nodes can block off the communications. You know, when you are moving and you need to know where is the best path from one point. For instance, this is one of our works that we did a cluster system. We have head clusters. The red dots are head clusters. Several drones or several mobile nodes can be in the range of this cluster head, and then they also move, and so you need to find the best path from this cluster head to maybe a surface vessel, and this is moving, and you need to establish the path. You need to transmit information. That is not a payload. This is just to organize the network. And the problem is we are scared about the point that just making the handshake can block the network. This is a very, very important point to take into account. Okay. And also, it was in Professor Sousa's presentation, is the concept of mule. Maybe we need to go back to the past. And I remember, and we talk about mule drones, just to carry information from one point to another. The mission of that drone is to carry information from one point to another. And that remember me When I was a kid and I read that novel by Jules Verne, it's Miguel, well, in Spanish, Michel Strogoff in French. And what happened? Someone cut the telegraphic lines and very, very old. You know, the first telegraphic cable between Europe and America was deployed in the 50s, but not in the 50s of the 20th century, but in the 50s of the 18th century. It's incredible. For me, it's incredible. Okay, someone cut the telegraph lines. What did the Tsar? He sent a courier on a horse, riding a horse. And maybe we need to go back to this kind of thinking for mobile networks. And the point here is AUVs, underwater positioning. I didn't mention in one of my slides, underwater positioning needs underwater communications. And underwater communications seem to be complementary and inseparable technologies. We cannot imagine one of them without the other. This is one example of application. This is a recent project that we did. We developed a system so that an underwater vehicle can know where it is, which so far it is not, up to my knowledge, that is not very easy to do. And what we did is we developed a kind of a GNSS repeater. So any number of underwater vehicles who are in the range of 4 of those 4 buoys that can be drifting, we don't need to fix those buoys, can calculate its position. Okay. This is the key issues. Well, this is a picture when these are the yellow buoys are our GPS. We use GPS signals, our GPS repeaters, and this is a small, very, very small drone. This is amateur drone that we use to demonstrate the concept that we were developing. But now, let me conclude my presentation with several personal impressions. Okay. First, there is still room to improve underwater communication, acoustic communications in terms of transmission technologies. But in my humble opinion, there is a little room for that. Okay, those companies will do better, but maybe not in capacity. They will do better in other aspects. Okay, maybe prices. This is maybe 100 euros, 200 euros. I bought several modems, simple modems, and I had to pay almost 6,000 euros a piece. So it's a huge difference. But when the market will be not mass market, because underwater will never be a mass market, but much larger market than it is now, I guess prices will go down, okay? But the challenges, for me, the challenges now are routing protocols that will make possible that the network will not collapse, just trying to establish paths from the whatever is underwater to the surface. A very important point is covert communications. This is, I think, from the point of view of defense, that will be very, very important. And the third point, that we need to do something that will be even a standard for a European standard or a world standard of underwater positioning that we don't have as we have GPS, Galileo, etc. And that's all. That is my email address in case you need students. Thank you. Thank you very much.
Thank you so much, Professor. Question from the audience? Yes, please, go ahead.
Good morning, Professor. Really nice presentation. I have ask a question related to the future of the communications underwater. So companies, like you mentioned, have tried to improve communication based on acoustic principle. But my question is, how you see the future of these communications, of this technology, or soon we will see a change on these trends for communications?
Also, Professor Sousa did, and I fully agree with him. I'm not I cannot see the future. Okay? If I was able to do it, who knows, I will play lottery or invest in the stock market. Are we going to live underwater? I don't know, but we are going to use resources. So that will, I think the market on underwater electronics will develop a lot in the next 10 years, a lot, okay? Also, the main point here is, well, the word is there is for a different reason, but the word is there is, we need to keep the ocean health. We are all of us agree with that. And that will need a lot of monitoring and maybe actions. And you cannot imagine those things without communication. It's like our life today is communications is not the important thing, but this is one of the most important tools for the way we live, okay? I don't know if I have answered your question.
Go ahead, please. The microphone.
Thank you, because it was really interesting, the presentation. I would like to ask if also is a challenge in the acoustic communications security, to secure the communications, because also is bandwidth consuming. I don't know if it's also needed to standardize that and so on.
Thank you. I think I mentioned it to one of the last, my personal points of view. The second one was what they called covert communications. That means that you cannot realize that someone is communicating using acoustic waves. This is one strategy, of course. But there is the classical one that is what we call steganography, and the other one is using encryption, cryptology. Okay, I think related to defense, that will receive a strong impulse in the next years. Okay. We have those two strategies, and I know very leader research groups are working on that. Okay.
So you have pointed out something important, in my opinion, to go to covert communications, not only in defense, because I would say also it may also be important in the civilian sector. Mm-hmm. Do you envisage any way to get to make underwater communications covered?
I think we will see it. I'm confident of that. Okay, but now I have a more philosophical idea about you know, I have friends that don't use WhatsApp. They say, I don't want I don't know, people up there to know what I'm doing, what I'm thinking, what I'm reading. And I said, you know, the best, I don't worry about that, because nobody's interested in Pablo Otero, you know, I am a little ant in this world, you know, and, you know, maybe it will be secure communications, covered steganography and cryptography will be needed in the civil world. Okay, that is a kind maybe of industrial copying, no? One industry from another, maybe that one. But
my point is really, at least in defense, when you are communicating, you are located, directly located. They know where you are, and that's important in defense, that they don't know where you are. So, for instance, you can in the aerial communications, you can use, for instance, direct sequence spread spectrum, so you can communicate below the noise level, and you cannot be detected.
You are fully right. You are fully right. But I remember, because I I used to work in Navantia in the past, and I was involved in these problems. And also from my engineer. I'm now a quite old engineer. Many times I receive questions from former students and things like this, and I always tell them, listen, operational solution maybe is better than a technological solution. Okay, so it is very important that nobody knows where you are, but they can know where you are not only detecting you. You know, we're talking about intelligence. I think, we have people here that are much better experts than I am in those fields. But I know that we will see covert communications in a close future. Okay.
Thank you so much. Coffee break time, so we can continue with ask questions in this environment, more relaxing. So thank you so much to our speakers. We come back in 30 minutes, 20 minutes? 20, 25 minutes, we will come back. Thank you.
En un mundo tan interconectado, la necesidad de entender y hacerse entender nunca había sido tan crucial. ¿Por qué Translate? Ofrecemos servicios profesionales de traducción en más de 200 idiomas para que tu empresa hable el idioma local y conectes con públicos globales. Contamos con la mayor red de traductores profesionales nativos y tecnologías de vanguardia. Por eso, podemos ofrecer una escalabilidad sin precedentes. Y brindamos una calidad incomparable. Así, la traducción no solo es precisa, sino también culturalmente relevante. ¿Qué cómo funciona? Basta con obtener tu presupuesto en nuestro sitio web.
Safely beneath the ocean's waves sits M-Wave. Bombora's pioneering patented technology harnesses the abundant power of the oceans to generate megawatts of clean, renewable energy. A series of air-inflated, flexible rubber cells, each 15 meters in length, are mounted to a concrete foundation. Out to sea, safely beneath the ocean's waves, sits M-Wave. Bombora's pioneering patented technology harnesses the abundant power of the oceans to generate megawatts of clean, renewable energy. A series of air-inflated, flexible rubber cells, each 15 meters in length, are mounted to a concrete foundation structure arranged to optimize energy capture. As waves pass overhead, the underwater pressure increases. M-Wave's rubber membranes are compressed sequentially, forcing air inside the cells into a central duct. Valves deliver a one-way airflow to the turbine, directly spinning a generator, converting this rotation into electricity. After passing through the turbine, the air is recycled to reinflate each membrane in a continuous sequence. The sustainable power generated by M-Wave is transferred to the electrical grid via a sub-sea cable. M-Wave's simple and modular design, with removable component parts, makes it efficient to operate and maintain. Its modularity makes it rapidly scalable and adaptable to both nearshore and offshore environments. Bombora, powering the blue economy with waves.
With climate emergency high on the political agenda, carbon emission reduction targets are becoming ever more stringent. Waves provide a huge renewable energy source, which until now have remained relatively untapped. Bombora, a multi-award-winning ocean energy company, has developed a unique and innovative wave energy converter called M-Wave to meet the challenges of harnessing this global, commercial and environmental opportunity. Bombora's patented M-Wave technology sits securely beneath the ocean's surface, making it invisible whilst extracting maximum energy. As waves pass over M-Wave, its flexible rubber membrane design pumps air through it.
So, how are you doing? How was that coffee break? Everyone is fine? Happy to have you here again, and happy to have the people from home. We're going to go with the second part of our first roundtable with Cecilia. Please.
Thank you so much. Welcome back after the coffee break. Now we are going with the final part of this roundtable. And the previous session we were talking about multi-agent system communication, and now is the time of bioinspiration. So bioinspiration plays a key role in robotics designs, as it allows engineers to create robots that mirror the efficiency, adaptability, and resilience of natural systems. By studying biological organisms, engineers can develop machines that solve complex problems with lower energy consumption and greater feasibility. Bioinspired features such as flexible structures, advanced sensory systems, and adaptive locomotion patterns enables robots to better navigate and respond to real-world challenges. Our next speaker is an expert on bioinspiration. Professor Shinya Aoi received the bachelor, master, and PhD degree in engineer from the Department of Aeronautics and Astronautics in Kyoto University in Kyoto, Japan, 2001, 2003, and 2006, respectively. He was with Kyoto University from 2006 to 2022. However, he is currently a professor with the Department of Mechanical Science and Bioengineering at Graduate School of Engineering Science at University of Osaka, also in Japan. His research interests include dynamics and control of legged robots and analysis and simulation of locomotion in humans and also animals. He received the Young Scientist Prize, the Commendation for Science and Technology by the Minister of Education, Culture, Sport, Science and Technology from Japan government in 2017. He also received the Best Paper Award at International Conference of Biomedical Robotics and Biomechatronics in 2012, and in the International Symposium of Micro-Nano Mechatronics and Human Science in 2018. So, Professor Shinya, welcome.
Okay, thank you very much for the introduction. I'm Shinya Aoi from the University of Osaka in Japan. First of all, I'd like to thank you for giving me the opportunity to attend this conference and also give a talk. And today I'd like to talk about the Gait generation of regular robot through neuromechanical interaction and bifurcation. And first, I'd like to introduce myself very briefly. And I'm from the Department of Mechanical Science and Bioengineering at the University of Osaka in Japan. And my study includes biomechanics, robotics, and system engineering. And I received my PhD from Kyoto University in Japan, and I moved to Osaka 2 years ago. And the University of Osaka is located here, here. Osaka very close to Kyoto in Japan. And this university is founded in 1931, and this university has almost 23,000 students and 3,000 teachers. And also it has 3 campuses like this. I'm in the Toyonaka campus, I'm in the middle one. And my study, especially focusing on the adaptive and agile locomotion in terrestrial animals. And these animals, including humans, walk in diverse environment. Humans walk easily even when there are steers, and this goat walk on a very dangerous and steep cliff. And also left down movie shows dog sports called agility, where dogs run through very complex obstacles. And this cheetah has very excellent physical ability and run fast to catch prey And animal locomotion is generated by skillfully manipulating the complicated, very complicated, and redundant musculoskeletal systems. And it's achieved through dynamic interactions between the brain, neural system, and the body, musculoskeletal system, and the environment. And this concept also applies to underwater animals. And we especially aim to elucidate this mechanism in terrestrial animals and apply it like the robot. And in particular, we're focusing on three approaches based on animals and models, and also robot. Specifically from the, sorry, I'll prepare the, it's okay. Specifically from the major data of animals, we extract characteristic structure embedded in locomotion and make hypotheses about the locomotion dynamics and control. And then we construct mathematical models and reconstruct locomotor behavior through computer simulations to evaluate the hypothesis and also to clarify the mechanism of locomotion in animals. And finally, based on these findings, we developed like robot to produce adaptive and also agile locomotion in the real world. And I'll show some overviews of our studies. The first is about human walking and running. As you know, we change these gait patterns depending on the speed. But these gaits have many differences. For example, during walking, at least one leg, one foot is always in contact with the ground. In contrast, running has a flight phase where both feet are in the air. In addition, walking is generated like an inverted pendulum, but running is generated like a spring. And to create such different gait in humans, a motor control hypothesis has been proposed. Specifically, linear combination of 5 sequential signals explains the motor command for muscle activity to walk and the change in the second signal, change walking to running. And to investigate this hypothesis about motor control, we use a very simple neuromechanical model, especially neuro, muscular, and skeletal model, like this. And through computer simulation, we investigate and achieve gait transition from walking to running, like this. It's very simple simulation, but from the walking, it actually achieves running behavior. Okay. And also, there is a very special device we call a split belt treadmill to investigate adaptation mechanism in human and also animals in locomotion. And specifically, it has 2 parallel belts, and the belt speeds are controlled independently. Therefore, this treadmill can create left and right asymmetric environment for walking. And especially when the speed is different between the belt, this is human walking, the relative phase between the left and the right legs shift from an antiphase, like this. We can adapt this kind of the very special environment. And also to investigate this adaptation mechanism in humans, we performed computer simulation of a neuromusculoskeletal model like this. Tide means the same speed between the belt, and the change to the split belt. Split belt means the left and the right, their speed are different. But this model can adapt to the environmental change from the sensory information and the motor sensory coordination. And not only this model simulation, we apply our findings to a bipedal robot like this. And tide means the same speed, and it changed to the split belt. I mean the defined speed between the belt. And this actually shows adaptive behavior during split belt treadmill walking. And not only humans, but also quadruped animals such as cat also show adaptive behavior in split belt treadmill walking. Therefore, not only a biped robot, we also use a quadruped robot to investigate adaptation mechanism during split belt treadmill like this. Now it's split belt. Okay. And also, we humans have achieved bipedal walking through evolution. But the origin remains unclear. On the other hand, these Japanese monkeys can achieve very excellent bipedal walking through training like this. And this Japanese monkey is a very useful model to understand the origin of human bipedalism. So we also construct a neuromusculoskeletal model of Japanese monkeys like this, and we perform the computer simulation to change gait pattern from quadrupedal to bipedal from the dynamic viewpoint. And also, we apply the finding from the neuromusculoskeletal model simulation. We applied a bipedal robot similar to the previous case, like this. First, walk quadrupedally, and stably change to a bipedal walking. So it takes time. Yeah, like this. And we investigate the animals and the models, the computer simulation, and apply to robot. But today, I especially talk about two topics. The first is about gait transition in quadruped robot, to investigate why quadruped animals change their gait pattern depending on speed. And the other is about maneuverable locomotion in many-legged robot. Many people do not like this, but this is to investigate how many-legged animals produce their maneuverable locomotion using many legs. So first, I'd like to talk about this first topic about quadruped animals. And quadruped animals change gait pattern depending on the speed, similar to human walking and running. But humans move the left and right legs in antiphase during both walking and running. But quadruped animals change gait pattern by changing the phase relationship between the legs in a very different way to humans. In particular, they use walking at low speed, like this, where each leg moves independently, like this, not synchronized. But when they walk at middle speed, they use trotting. In this gait pattern, diagonal legs are synchronized like this. Very beautiful. And but when they walk at high speed, they use galloping. We can see in the horse race. In this case, left and right legs move almost simultaneously, like this. However, the mechanism of the gait change in quadruped animals remains largely unclear. And I'll show a movie about the experiment of this cerebrate cat. In this cat, a portion of the cerebellum is removed. And the body is fixed and supported by this device, but the legs are free, and the feet are put on the treadmill belt. And when the belt speed moves like this, then this cat begins to walk like this, in the absence of cerebellum function. In addition, when the belt speed is increased, this cat changes gait pattern, especially start running like this. Because the spinal cord is intact in this cat, this suggests that the gait transition is induced by local sensory feedback from the feet. So we aim to investigate this gait transition mechanism induced by sensory feedback using a very simple quadruped model. And this is a very simple body mechanical model composed of one body and 4 legs. And each leg is connected to the body by a pitch joint. And the leg length and the joint have springs. So it's very simple structure. And this figure shows a neural control model composed of phase oscillators. Each leg is controlled by one phase oscillator. And this phase oscillator produces the desired leg motion like this by controlling the leg length and the joint angle like this. It's a very simple equation. And this leg motion is controlled by springs with a desired motion similar to the PD, I mean the proportional and derivative control in robotics. So it's very simple control. And the neural system receives sensory feedback. Especially, each oscillator receives actual leg length. Just this information. And the phase, we use the phase oscillator for the controller. And the phase dynamics of the oscillators consist of a very simple one. Only the basic gait frequency and sensory regulation, just 2 terms. And we use the error function between the desired and the actual length to regulate the locomotion rhythm in the oscillator dynamics like this. So this is also a very simple equation. And although this model has 4 independent oscillators, but we fix the left and right legs in antiphase. In this case, the gait pattern is determined only one parameter, very simple, especially the relative phase between the fore and hind legs. In particular, walking pattern is generated by pi over 2, like the left one, and also the trotting at the middle speed is generated by pi, like this. And using this very simple quadruped model, we perform the computer simulation like this. As a result, when the gait frequency is large, so very fast, then the walking changes to trotting like this, without changing any parameters. Yeah, now it's walking, and around here, change to trotting automatically, without changing any parameters. In contrast, when the gait frequency is small, in this case very small locomotion, then trotting is changed to walking automatically without changing any parameters. And here. Namely, different gait transitions appear depending on the gait frequency. This is the result, but we want to know the mechanism. So we investigate the mechanism of these gait transitions under the assumptions. The body rotations and also leg joint angles are small. Because the left and right legs move in antiphase, at least one leg is always in contact with the ground in both fore and hind side. So the equation's motion of the center of mass height is given like this. It's very simple. Just acceleration and the force and gravity. And by regulating this equation, we obtain this like this. In particular, this omega n explains the natural frequency about the center of mass height. And in this equation, we obtain the stationary solution like this. It's very simple type. And based on this stationary solution, we obtain the phase oscillator dynamics like this. Also, it's very simple, just using the two terms about the basic oscillator frequency and sensory regulation term. And we obtain this using the stationary solution, X hat. And by using the relative phase, this delta, then we obtain the governing equation of the relative phase. And especially the right-hand side, the sign of the right-hand side changes depending on which of the natural and gate frequencies larger. And the pi over 2, namely walking in the blue, and also pi, namely trotting, are both the equilibrium solution of the governing equation of the relative phase. And this indicates that when the gate frequency is small, walking is stable and trotting is unstable. And this induces a gate transition from trotting to walking. In contrast, when the gate frequency is large, then it changes to trotting is stable, but the walking is unstable. And this induces the gate transition from walking to trotting. So completely opposite. So we obtain from the dynamical analysis about the stability and why gate transitions appear and why different gate transitions appear. So to verify this result in the real world, we developed this very simple cutoff robot. And we confirmed that when the gate frequency is small, the locomotor behavior is not so good, but actually the relative phase change from trotting to walking like this. This is the case when the gate frequency is small. And in contrast, when the gate frequency is large, then the gate transition change from walking to trotting like this. So it's completely opposite result. And we verified the result about the dynamical analysis using the actual robot. Okay. So next, I'd like to talk about the second topic of the many-legged locomotion. Using many legs like centipede provides the ability to avoid falling down and tread leg damage. So it would be useful for legged robot. And the centipede arthropod with a pair of legs on each body segment. And they have at least 15 pairs of legs, and sometimes more. And they flex their body segment and move their legs, generating body undulations. And they change the gait pattern depending on the speed, similar to quadrupedal animals and also humans. Specifically, body undulations are usually absent at low speed, but appear at fast speed. And amplitude and wavelength increase at the speed. So please watch this movie. Resolution is not good, but I think you can confirm that the centipede change the gait pattern depending on the speed and produce very large body undulations at high speed. However, it remains unclear why they create such body undulations, because they have legs unlike snakes. They do not necessarily have to produce body undulations. And actually, there are biological conflicting hypotheses. The first said that they actively produce body undulations. And the other said that they resist body undulations, but fast walking creates these undulations. And in this study, we especially focused on the second one. They do not want to create body undulations. So to investigate this, we especially developed a robot model composed of 6 body segments and 12 legs like this. And the body segments are connected by yaw joint with torsional springs to resist body undulations. And we perform the computer simulations like this. Then this robot walks in a straight line at low speed, and also with high spring stiffness, namely the low spring compliance. However, body undulations appear at high speed and also with low stiffness, namely the large compliance like this, similar to centipede. Because we use just spring, we do not motor about the body axis. This is just a result from the passive dynamics. And to verify this computer simulation result, we also developed the centipede-like robot like this. And this robot walks in a straight line at slow speed and with low spring compliance, similar to the model simulation, just walk in a straight line. In contrast, body undulations appeared at high speed and also with high spring compliance, similar to the model simulation. And also, this is just a demonstration, but also the robot walked in a straight line at low speed and with high spring compliance. Body undulation appeared over a critical value. In particular, the amplitude of body undulations increased as the speed and also spring compliance increased like this. So, sorry, just that, it's okay. And this result means that the split walk is destabilized at critical value by increasing the speed and also spring compliance. And the body undulations of the robot are generated by hop bifurcation. And also, when all the spring compliance was increased, the body undulations appeared by hop bifurcation. But when only the spring compliance of head module was increased, straight walk is changed to curved walk by pitchfork bifurcation, namely the different bifurcation, like this. And also the curvature depends on the compliance, like this. And this movie shows the curved walk with very small curvature like this, without changing any parameters. And also the bottom movie shows the curved walk with very large large curvature. We do not use any reference such kind of the curved walk. This is just a result of the dynamics. And also here we discuss the centipede locomotion again. In this movie, only foot contact points are shining. Okay, you can find that. They are shining. And also, these yellow circles show the foot contact point at a moment. And this means that many legs are in contact with the ground to support the body during locomotion. And also, these legs are constrained on the ground because they support the body, and which can make maneuverable and agile locomotion, such as quicking turn, difficult. But the actual centipede show very maneuverable and agile locomotion, namely the mechanism to produce maneuverable and agile locomotion using many legs remains largely unclear. And not only the centipede, also you do not like this, but the cockroaches. It's not actual, well, just I like draw. Cockroaches also show very maneuverable and agile locomotion like this. And there is, to investigate the dynamics of the cockroach locomotion, very simple model, right one, has been proposed. And this shows that the straight walk stability change depending on the position to receive the ground reaction forces, like this. And when the straight walk is unstable, the model cannot continue straight walk like this. I mean the right part. But by comparing a quick turning task between the stable and unstable cases, we found that thread work instability help maneuverable and agile locomotion like this. I mean, the very quick turn. And as well as cockroaches, aquatic animals such as sea lion also suggested to use instability to enhance maneuverability. In addition, not animal, but fighter aircraft such as F-16 are designed to be aerodynamically unstable to improve maneuverability. And because our robot also has a thread work instability, so we installed variable stiffness mechanism as a head module, only as a head module like this, to control the thread work instability and bifurcation during experiment. And as a result, autonomous sequential turning tasks were achieved by changing spring compliance to create curved work with appropriate curvature through pitchfork bifurcation like this. There are many sequential targets, but this can follow the target just using the change of the dynamics, I mean the bifurcation, by changing the curvature of the behavior. Okay, finally, I'd like to thank you for the collaborators. Thank you very much for your kind attention.
Yes, go ahead. The micro, please.
Thank you. Really fascinating talk. I have a lot of questions, but I will only ask one. Have you looked at the mechanism that could provide changes into locomotion when you consider bipeds or quadrupeds or multipeds walking in water?
Walking in water?
Yes.
I think that in terrestrial locomotion, gravity is very important because we walk using the kind of the inverted pendulum, and running is a kind of the spring. But underwater, and also we study about the low gravity in the space. In that case, also gait pattern change. Not they use walking, but running very change. It's very difficult to prepare the double support phase because the gravity is very low. In that case, we cannot walk, so we especially use running. But running has also many differences, especially using the different, I mean, the kinematics not so change, but especially the contribution of the muscle change so much because almost the gravity is decreased. So in humans, it's very important to balancing. Balancing is important thing, the contribution to against the gravity. But so low gravity in the space, such kind of the contribution it becomes low. So I think the underwater also some similarity between the low gravity on the space, I mean the planet or something, on the moon or Mars. Maybe many people will go in the future. Okay.
Professor, really nice talk. I just wanted to know if you only told about torsional springs or springs in general, but most of humans and animals also use damping. Have you considered to use it or implement it in your experiments?
I think especially we use the muscles. Muscle has a kind of the passive spring and also active part. I think the balancing. The kinematics and also dynamics is very important. To simply investigate the contribution of the dynamics, spring is very easy to understand. I mean the very simplest model. Also activity of the muscle can be contributed as the springs. But very, what should I say, to create the locomotion, not only walking and running, the balancing of the dynamics in the passive part and the active part, especially the contribution of the neural system, not only the feed forward, but also the sensory regulation. So I think depending on the study, I mean the locomotion, we have to change especially specific topics. So I think the most simplest case is just using springs. But the spring stiffness and also the neutral position could be changed by sensory regulations. So such kind of interaction also important. So I think not only the springs passive part, but also the active part also important. So yeah, and not only humans. Humans is just against, as I said, just against the gravity. But not only centipede, but the cockroaches do not erect, just only walking on the planes. So I think depending on the situation, I think the important dynamics could be changed. Okay.
Thank you. More questions? Yes.
Yeah, you have explained several patterns, bipedal, quadruped, and do you have conclusions about what models are better for what uses, or the utility or applicability of each model? So maybe there are, I suppose there are advantages and disadvantages of each type of walking.
So you mean for humans?
No, for
animals. Animals have many structures.
What are the applications of this? I mean, how to apply, if for a specific application is better biped, or for this application is better quadruped, or whatever. Do you have conclusions about that?
No conclusions, because animals has many varieties. Depending on the structure and also the contribution, such kind of energy consumption and also stability, depending on the situation, the optimal locomotion type could be different. So I think for humans, we can walk bipedally and also quadrupedally using the forelegs. But I think we also learned to use bipedally, and it's very, what should I say, it's energy optimal. But it's very unstable. So I think depending on the balancing, stability, energy consumption, and when we walk bipedally, we can use hands. So I think depending on the situation, the optimal gait pattern and the situation could be changed. I think.
No more questions. Thank you so much, Professor Shinya, for the talk. So, Iago, please.
Thank you very much. Please open the mic. It's open? Okay. Thank you very much to all. Thank you, Cecilia. Thank you, Professor Shinya Aoi. We're almost ending our first roundtable. Let me say, I'm sad to announce that Stephen Williams, our fourth speaker, couldn't be here right now because his flight was canceled, but he's trying really hard to get here for tomorrow. So we'll reschedule his presentation, and you will have the opportunity to speak with him about underwater unmanned vehicles. Okay? Stephen, if you're seeing us by YouTube or Twitch, thank you very much for your effort. So, it's been an amazing morning. We have spoken about the importance of communication to do everything with underwater vehicles. We have spoken about the challenges of the environment and the challenges of controlling a swarm of robots with Mr. Joao. And now we have spoken with Mr. Shinya about the challenges to develop a system that can replicate bioinspired movements. This is amazing. For me, that I'm not an expert, this is something that I will never expect. But we have more. This is the first roundtable of 6 in total. So now I want to offer all the people in the room to go outside and have lunch. We have a specific lunch for the people with specific needs or specific diets. So you have to ask for your own dish, okay? And for the people that is in home, we're going to offer you an static image where you can see the agenda. We're coming back at the planet timetable. So, Thank you very much, and let's continue with the Twilight Conference. Bye.
Out to sea, safely beneath the ocean's waves, sits M-Wave. Bombora's pioneering patented technology harnesses the abundant power of the oceans to generate megawatts of clean, renewable energy. A series of air-inflated, flexible rubber cells, each 15 meters in length, are mounted to a concrete foundation structure arranged to optimize energy capture. As waves pass overhead, the underwater pressure increases. M-Wave's rubber membranes are compressed sequentially, forcing air inside the cells into a central duct. Valves deliver a one-way airflow to the turbine, directly spinning a generator
Bien, estoy aquí con Killian, a ver.
Iago, al final se hace, ¿no?
¿El qué?
Es su podcast, que me he preguntado por él.
No sé. Mañana. Hoy está el Pera. Hi, Killian.
Hello.
Hello, I am here and we are trying that the FAO can join us to make the final test. I can show you, I don't know if you see the conference room. Wait a moment. So this is conference room, and you are going to be there when you, okay? And I hope they can make it with Teams and with presentation. I'm sorry.
Cool. No, it's my fault. Sorry I couldn't make it in person. But...
Yes, Killian. I'm going to ask them how... Bruno, ¿tenéis el Fermín? ¿Tenéis ya el link? ¿Tenéis el link? ¿Os lo ha mandado Bruno?
A ver, el Bruno que me habéis mandado. Sí.
¿El de Teams?
Unirse a una reunión ahora, ¿vale?
Os he metido una reunión de las 5:20, que es cuando habla él, y otra ahora que pone test. Es en la de test, ¿vale?
Y ahora vamos con el siguiente, es Daniel González.
Si haces la prueba... Sorry, Killian, wait a moment. Sorry.
La salida salimos por HDMI, si nos atendemos aquí.
Sí, porque esa es la salida. No, pero ese es el audio, sí.
Esto es el audio.
Vale, pero Javi tiene montadas también todas las otras radios, ¿eh?
Vale.
Hi, Mokarram.
Vamos aquí. Porque la imagen de él, ¿dónde la tenemos?
Aquí, pero va a ser más fácil porque se cabe de equilibrar el resto.
No, pero es que se lo coge
¿Te coge la...?
de la correa.
A ver si eso funciona. Por aquí.
Claro, es un HDMI.
Sí, me están dando. Yo lo tendré aquí.
Vale,
A mí
sí,
me
sí.
entra.
Vale, sí, sí. Y lo único que tendría que entrar es el micrófono.
Sería la tarjeta sonido que no la cogen. O sea, no la tarjeta sonido.
Sorry, Killian. Os acabo de admitir.
Ahí, entrada. Hola.
Hola.
Yo oigo.
Hi, Killian.
Soy yo el que me oigo. Hola. Yo digo, joder, que bien habla. Que bien hablo inglés. O sea, lo que ha llegado la inteligencia artificial. Vale, varios micrófonos.
Hi, Killian. Can you say something, please?
No me deja instalarle la... ¿Está encendida? Sí. Es la 4. ¿Sabes dónde lo instalarle? Es que no tiene NDI tampoco. Parece que es la Gen 2. 4, 2. La comprar primero. Right, porque la generación 2. No, me está saliendo la 4ª generación, pero la bajamos a una generación superior. ¿Sí? Eso de que me vaya el gallo por atrás. Sí. Live Sound, estudio recording será, ¿no? No sé. Página web. 4 y 4. Está. Por la generación, ¿no? Ya voy a buscar la 4 y 4. 4 y 4, tercera generación.
No, estamos haciendo la prueba con Killian, a ver si funciona. ¿Cómo? Ah, vale. Pero mañana pueden... Killian, speaker. 1 moment. I'm going to check that and then it's okay. Hello, hello, hello.
Hello.
Now. It's okay. Wow. Okay, that's nice.
Hello,
Hello,
Killian,
Killian,
can you hear me now?
Yeah, I can hear you.
Okay.
Can you
talk?
Hola, 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 hola. Hello, hello, hello. Hello, hello, hello. Killian, can you say something, please? See, Killian again, sorry. Can you say something? Killian, do you have your microphone mute or are you okay? No, it's okay. Okay, wait a moment.
Patricia, can you hear me? If it doesn't work, hello? Hello? Can you hear me? Can you hear me? Great.
Yes, now it's okay, Killian.
Okay, great. So shall I try sharing my screen?
Yes, please. Yes, it's okay, Killian. We
Okay,
can
yeah.
see all, really nice.
Yeah, and that's still
Yes, that is
good
nice.
now? Okay, perfect.
Perfect now. I think I'm going to show you, sorry, Killian, that you see when you please share again so you can see how. We are going to use, Killian, we are going to use this link, this test link, okay?
Okay.
I create another event, but please forget it. It's
join this
better
one,
that
yeah.
you use this link.
Okay,
Okay, thank you, Killian.
thanks.
So I think it's okay. I think we can close the test. Then I see you at 5 o'clock. We can connect with you, and when the other speaker finish, I will chat with you to say you come inside the conference.
Okay.
Thank
All
you
right,
very
thank
much.
you very much.
Thank you very
Cheers.
much. Thank
See
you
you
very
later.
much, Killian. See you later. Thank you.
Out to sea, safe. Out to sea, safe.
Welcome back to the Twilight Conference. How are you? How was that lunch? How was that moment to have a little bit of calm and some networking? Did you make yourself sure that you speak with someone? Did you find a new colleague, a person with opportunities for a collaboration? Yeah, I see Mokarram here is saying yes. Okay, that's the main goal of everything that we're doing here, so that's right. We're starting the second part, the second roundtable. Thank you very much, Daniel García González. She is a researcher from Universidad Carlos III de Madrid and one of our main collaborators in Monodon. He was part of the soul of this conference. He was the scientific advisor of everything that's happening here. So we're so happy to have you here, and the stage is yours. Thank you, Daniel.
Thank you very much, Iago. Well, first of all, just would like to say that it's not only me, but also Abdon that was quite involved in all this organization. And I have to say that it has been a pleasure to, well, collaborate with you guys from Monodon. And I think this is kind of, well, excellent environment and excellent opportunity, not only to develop and create connections, right, and new collaborations, but also to have this kind of really needed field that is not only what we are doing in our specific field, this is also what we can learn from other fields. And I think this is like ideal conference, right, to have all these new methodologies and see how we can create connection and how we can implement different methodologies in our fields or exploring new fields. So that said, I want to start with a presentation of our great 3 new speakers. So now we're going to change a little bit the topic. This roundtable 2 is called Soft Materials, Sensing and Novel Approaches. So we will have Professor Hirai that, well, he's going to say about hands, right? Yes. Robotic-like hands. Then we're going to have Concha that she's going to tell us a little bit about soft robots, soft actuators, soft sensors. And then Mokarram is going to complete the session with, well, some, I know your word well, electro-active and multifunctional materials. So how is not only structural, but we can have in the same component this multifunctional, well, development. So let's start with Professor Shinichi Hirai, so professor at the Department of Robotics at Ritsumeikan University in Shiga, Japan, director of the Soft Robotics Lab, Hirai Lab, and he investigates robots with novel functions brought by soft materials and its related technologies, including soft sensors and actuators. For the last 30 years, he has been in such university, but he was also visiting researcher at MIT, right, and assistant professor at Osaka University. So he has many papers, many awards, and I'm pretty sure that, well, we're going to be delighted with your presentation. So all room yours, and thank you very much for joining the conference.
Thank you for the introduction. Okay, so, the microphone? Oh, yeah, here. Okay. Thank you for the introduction. So my name is Shinichi Hirai, from Ritsumeikan University. First of all, thank you very much for the organizers to invite me to this fantastic conference. Okay, now I'm talking about non-electric soft robotic hands for underwater grasping and manipulation. So, okay, but first of all, let me talk about a little bit my university. I'm now in the Ritsumeikan University, one private university, originated from Kyoto. Now, I'm not in Kyoto now. I'm in a Biwako Kusatsu campus. It is next to Kyoto. 15 minutes by train, very close to that Kyoto. And also the Biwako is also the name of the lake. It is also the largest lake in Japan. So very beautiful, also surrounded by mountains. So now, almost 30, just 30 years ago, our campus was established, and also soon the Department of Robotics was established in 1996. I was involved in the Department of Robotics so far. Okay, so now my lab, the soft robotics lab, We are now investigating robots with novel functions brought by soft materials. So the soft materials and also soft structures. And also we are working on the related technologies, including soft sensors and soft actuators as well. So today, I'm talking about the manipulation of living organisms. We are now developing the various soft hands for grasping and manipulation of living organisms. So I will introduce our works. Okay, so the background, we have many grasping and manipulation of underwater organisms. So in fishery, in sampling, and also and so on, and also in aqua museum also. So we have many such kind of operations. So in such operations, we need robot hand. Okay, but electricity, you often use the electrical motors to drive the open and close robot hand. But the electricity in water often causes these several problems. That's why now we are focusing on the electric-free hands. I mean, the robotic hand, without the electric driving. Okay, so to do so, but first, we just here this from Wikipedia. We just categorize. We find that we find the living organisms in water can be categorized into the newton, plankton, nekton, and benthos. We have tried to develop the robotic hand for these categories. Our idea is to use the environment around the living organisms. Okay, we now here focus on the benthos, living creatures, on the bottom, near near the bottom of the sea, and the plankton, the drifting in the water. So the idea here is to use environment, around benthos and the plankton. Here, the benthos, we focus on the contact because they are living in near the ground, the bottom of the sea. If you have something approaching the benthos, robot hand may contact with the bottom of the sea. Why don't you use the contact to drive the robotic hand? And plankton also, that's the drifting in water. If you approach robotic hand near plankton, water pressure, water resistance may cause. The idea is to apply water pressure, water resistance to drive robot hand. Okay, so let me here. I'm talking about first the contact-driven hand, and the origami membrane hand, and also water pressure-driven hand. For these, the living creatures. Okay, but first of all, we are now focusing on the benthos, the living, the organisms, the on was near the bottom of the sea. To grasp such creatures, living creatures, we developed the contact-driven hand. It uses. We have here we have robotic hands, the back ones, the consistent of the several fingers, and also we have now the kind of the object, on the table. The idea here is to open and close. Using the contact force, when the finger contact with the touches to the ground. Okay, let me show the motion behavior of this hand. Okay, here, that's now closing. opening. Okay, here we have no actuators, no sensors in the hand, fingers, just only the mechanism. So of course the hand is moved by the robot manipulator, but the open and close are driven by, realized by the contact with the ground. Here, okay, so here like this, and also the closing, from opening, also that's driven by the hand. Okay, so this mechanism is quite similar to such a pen, you know, we can push something. Okay, so we have another state, and push again, we have move to the original state. So this is so-called the bistable mechanism. So we have apply such kind of the principle to this robot hand, Okay, so structure is very simple. So it consists of two parts mainly. So first here we have this one. So this is the link structure. So the several links are connected. So in series, and also we have the elastic. So the kind of the plate here, and we have in the top here we have the kind of the hole, and also hole here, and also a protrusion part here. So, okay, so in open state, okay, like this, so we have it's a connected part, so the link structure here, and so the elastic, so the sheet here. So if you push, that's if the finger contact with the ground at the top, so it's quite difficult to control the position. Okay, mouse. Okay, so this part. Okay, so okay, you have to push this part. Okay, so this part moves upward. Then we have the hole here. Then we have also here. So that's kind of the nail here. This nail is inserted in the hole. This is a closed state. And also, if you have the push again here, so this part, so the slide from the hole, then we can open the finger. So okay, so they have a protrusion and also the notch. So based on this, the structure, so we have just by contacting, so we have the kind of straight, so the state and also the curved state. Curved state can be realized, through the contact. So they are driven by the contact. So here is a more detailed one explanation. But first we have the closed. It's an open state. So it's straight. Then here, if the finger is pushed, so the finger is contact with the ground. So this part, so somehow inclined. Then this nail is inserted in a notch. Then again, if you this is locked state. So again, if you have contact, then here, this part, again, moved up. Then this is the protrusion part, so it pushes this sheet. Then this nail, is now free state. Now this is an open state now. Again. Okay, and also unlock. We have in the reverse state we have the unlocked state now. So this is the first prototype. So the robot hand. We have maybe 8 fingers. Also the fingers driven by the contact forces. So this is kind of the simple experiment. This is the sample of a jellyfish. So made of the gel. Okay, again, here. Just pushing. Okay, now open. Just pushing. Now it's closed. Again, pushing. It's open again. so we can so the transit so from so the open, close, and close to so the open states. And also we have as experiment so the here. And this is not a so the living organism, but a pudding. Okay, you can see here. Some are so the broken, but anyhow, so we can so the glass bit, glass pudding, and also the release the pudding again, like this. Okay, again, so we have no actuator in this hand, no sensor, no actuators, no sensors, just as we have also the mechanism, locking and unlocking mechanism alone. And also we can so grasp many things, octopus egg, again, like this, and so on. Okay, so this is another one. Okay, here you can see here, so because of the fingers are made of so this is a failed one, so sometimes so it fails because of so sometimes so here, so this is somehow so broken, it's so hinders, that's so the opening. So because of now, so the initial one, so consists of the rigid rings connected by bolts and nuts, so it's somewhat complicated. So we have simplified the fingers. So okay, instead of so the rigid rings, we just so replace the rigid rings. So by so the flexible link. So also so this is so printed. So using 3D printer. The principle same. So but so it works well again. So here. Also the most simple. So the structure is very simple. So now it consists of 2 parts. Okay. So also both are so 3D-dimensional print, 3D printed. Oops. And also okay, so this is so can grasp some so much thinner. This is the vegetable. So okay, so because it is so curved, so inside. So once we have so contact with the ground, so it can scoop out. That's so such kind of so thin target, like this. And also, okay, we tried many of the experiments. So the sesame, because we have designed so the finger shape. So okay, so in the open, in the so the closed state, now we have a so the small gap between neighboring. Okay, like you can see here, in the closed state, we have a so the very so the small gap between the neighboring fingers. That's why so we can so pick up such kind of so the granular materials also. This. Okay. Okay, so this is the contact, so the driven robotic hand. Okay, now so we want to so step on so focus on the plankton. So drifting in the so water. So the idea here is to use, first of all, so again, so scoop, so such kind of plankton, so with water. So we now so here, so we developed so origami membrane hand. Okay, you can see here, this so hand, so consists of so origami, so origami, so membrane, driven by also the contact-based so mechanism. So the idea here is so just by enveloping so such kind of origami membrane, we can so grasp the plankton with water. So the idea is speaking bodies with liquid. So here, of course you can use the ladder, but it often moving. Sometimes the water drops, and also water flow. There are in this case beads, planktons. That's why we developed another approach. To membrane-based hand. Okay, so this is our origami membrane hand. It consists of the origami membrane below, and also the vessel, the in the upper part. Okay, so if you saw this is the open state, so the left, right side, right, we have this is a closed state. Just pushing down the top plate beneath. This is closed. We can close. That's the hand. Here we use as a cresting pattern. It's a famous origami pattern. It's like this. We can here. The open state. The closed. We can move. We can deform. Such kind of pattern like this. From the polygonal prism to a flat shape. We have the fabricated membrane. Via using the liquid silicon printer. Here this membrane was made of the silicon, liquid silicon. It's based how to say based strong. Even if you have printing by hand, it doesn't it can stand. By humans such kind of motion, humans such kind of forces. And here we have these are the lines. That's the four lines. You can print out such kind of structure using the 3D printer. Like here, this is the motion, deformation of the membrane. In the open state, this is the bottom of the face. In the open state, we have the hole, at the center here. But once it's closed, deformed, the bottom is completely closed. We can keep the water. Inside the membrane. Here, we're now testing, demonstrating. Now we are picking floating bead with water, and pressing right vessel like this. Again, here also we have used the contact driven structure, to open and close the membrane. The difference you can see here. We have basically no very little the water drop, and also we have the small disturbance to the floating bead. But here, this one, but here, in this one, we are now using the contact base, again, the contact base, contact-driven mechanism. It means that so we can apply this structure near the bottom. In water, far from the bottom, we cannot apply this robotic hand at all. So that's why we have also developed another robotic hand plankton to apply to use the water pressure, water resistance to drive the hand. So this is the motion. You can see here. The open and close can be performed by just by during moving down. Moving down, it opens, and if you move up, the fingers are crossed. So this is caused by the water pressure. Okay, so the idea here is we have the water resistance panel, and we have a finger, elastic finger, short fingers, and also we have a base here. So the base and the panel are isolated, connected by the elastic fingers. So if you apply force to the panel from upward, then the fingers will bend inside. Then we apply the locking mechanism also at the tip. Then we can lock the fingers. And also in air, in contrast, if you have air, we have such kind of closed state. Then if you moving down, now the force the upward is applied to the upward. Then this also this force will open the fingers because the resistance panel will moving up. And also this is kind of the principle of open and closing the fingers. And also we have also designed the locking mechanism at the tip of the fingers to ensure the closed state. So we have such kind of structure. Here we have the concave region and the protrusion at the tip of the fingers. This is the this is the kind of the animation here. So once the fingers meet one another, the finger, the tip will the protrusion will guided inside the concave region. Then it will locked in the such kind of round region. Then we have locked the state here. And also in this there's a locked state. If we somehow twist that's the plate, we can easily unlock that's the fingers. Then we have putting the rotating plate on one side of each finger to realize such kind of twisting motion. Okay, this is the prototype, the finger part. We have the elastic finger, also printed in using the silicone rubber printer, and also the locking mechanism. And also the rotating plate. They are put to the tip of the fingers. Okay, this is the tip of the finger. Somewhat complicated, but anyhow, we have the locking mechanism, blue one. And also the rotating plate to twist the fingers to unlock the fingers. Okay, here's the base and so the water resistance panel, so the upward. Okay, so the group itself. So the base and so the water resistance panel and so the fingers and at the tip, so you have also the mechanism, locking mechanisms. Okay, so here you can see here, here. At the first time is open and close, open and close. Okay, so just pushing down to the open, so the moving up, so this so the closed. Okay, here experiment setup. So here we have also again so the put this finger robot so the on the top robot, so they have so the conduct experiment here. Okay, this is open. Closed and locked, so the like this. So the now so the fingers are locked. So the one another, and so the just so the moving down quickly. Then so we can so the open so the finger. So we are using such kind of water so resistance to open and close the fingers. And also, we find that okay, so in this case, so in this hand, so the velocity is very, very so the critical to realize so the open and close and locking and unlocking. So if you have so the appropriate velocity, we can so the successfully lock the fingers. But so if the velocity is slow or kind of fast, it doesn't work. So it depends on so the structure. And this kind of experiment, so okay, we have also something target in the water. Now, so it can so pick up successfully. But unfortunately, okay, in this case, we cannot release it. So this is because so the target weight, weight, so affects the result. So we have somehow the lighter one object target, so we can so successfully release the object target like this. So now so depends on so not only so the speed but also the weight of the target. So now we are so analyzing so this phenomena. So by using so the mechanical analytical model. Okay, so here, so now here we have introduced the robot hand, so the grasping, so the underwater organisms, so the contact-driven first one hand for benthos, and the origami membrane hand for plankton near bottom, and so the water pressure-driven hand for plankton. So now we are analyze, we are now designing these hands to realize more stable grasping and releasing. And also they were now analyzing the behavior of this hand using the physical models. Okay, that's it. Thank you for attention.
Okay, so thank you very much for the next presentation. So we have time for some questions. Have some of them. Not sure if. Okay, maybe I can start. Well, I have several questions because this is quite interesting. So my first question is regarding the design of all these systems. In the end, you have many instabilities, right, to induce actuation, etc. How do you design that? Is trial error, or do you have some computational models, something like that?
Currently, it's a trial error. So we have basically okay. So we have the design. We have design kind of first prototype. We test it. Then we find out okay, kind of the stability or kind of the performance.
Okay.
And also stability. Then the design. That's the finger. Also, we're now building the mechanical model, analytical model.
Yeah.
And we are doing the computer simulation as well. but it requires much time now. That's why now mainly we're now using kind of trial and error approach.
Well, I think you should meet these guys at some point. They're going to present tomorrow because they have a nice spy. Really nice method. So, any question from the audience? Okay, here, Fabrizio. I have more, but...
Thank you. Really fascinating talk. I have a question related to the last device that you showed, and probably is slightly linked to the comment about the instabilities. Have you noticed any specific effect given by the speed or the impact to the water in terms of really of efficiency of the device?
Actually, you're right. Here, we have tested how the velocity, how that velocity affects the locking mechanism, and also unlock also maybe the impact with also the affect this unlock mechanism. But we have not just now tested the preliminary level, in a simple level. We have not talked now here. But you're right. The impact, the complete affect, the unlock the behavior.
Just commenting on that, I think this is quite interesting because you will have two different mechanisms. So first the impact, second viscoelastic effects. Viscoelasticity, so essentially the materials have different stiffnesses and there's different actuation rates. So in the end, you have some relaxation that can introduce some shift into the instability. I think this is kind of super nice area to explore. Any last question from the audience? Sure.
I'm part of the audience, right? Well, very inspiring. Thank you very much.
Thank you.
So you don't think you should integrate any type of sensors or for instance, right, to improve your mechanisms?
Okay.
So where is the limit if you think there is a limit?
Okay, so it's kind of a extreme. Okay, it's the first step. We have now no actuator, no sensors. Okay, one idea or kind of extreme. But of course, if you introduce the sensors, what kind of simple mechanism, for example, the kind of water pressure sensor or something, and the mechanism driven by water pressure, might be improve the stability or kind of or opening and closing. So. Right. And also now currently, also kind of MEMS-based, for example, MEMS-based kind of structures are available. Now, we want to apply such kind of small mechanism here. Then I feel not sure, but I feel it can improve the
very nice
performance.
Okay, thank you very much.
Thank you much.
Okay, so please, thanks again, our first speaker. Thank you very much. And now we're going to move to the second talk of this session. So it's going to be delivered by Professor Concepción Monje, Concha, and it's going to be on novel approaches on robotic actuators and sensors. So I have to say that Concha is from my same institution, but although we knew each other somehow, this is the first time we met. Thanks, Monodon, for this opportunity. So Concha is director of the Center for Aeronautical Training and Services of the Universidad Carlos III de Madrid. For more than 20 years, he has been working on different research projects on robotics and robot control, especially in fractional order controllers for the control of flexible manipulation. And she has large experience in the field with more than 100 research papers in high-impact conferences and journals. So please, floor is yours, and I'm pretty sure it's going to be fantastic.
Okay, thank you. Thank you very much for inviting me. My pleasure to be here. I'm just sharing some of our ideas and solutions from my lab regarding soft actuators and sensors, and also robots that we can apply for real problems, right? So I'm going to start saying, when all this started from our side, because we come from the humanoid robots field, right? Which are quite rigid and quite limited, as you may know, right? So the idea is, okay, we have this, let's say, hard structure, and we want to improve some of its joints, right? Because it's clearly rigid, and in some cases it breaks, right? We have some experiments in which we can see that the robot is breaking. Apparently, there is no reason behind the breakage, but of course it is because of the hard materials composing the robot. So one day we decided why not to research a little bit on soft joints for this robot. And the first idea was to replace the neck by a soft soft link acting as the neck, right? And later we can see how this has evolved into a soft arm. And we will discuss from that solution, other solutions coming next, right? So the idea was, first of all, okay, to design the neck, the continuum, right? But also, there is a constraint for us, and we need to be sure that the solution must be, or needs to provide accurate positioning. Right? Maybe in some of the examples we can see today along the session, the accuracy is not needed, not required, but if you use it as a robot, as a humanoid, for instance, you need accurate positioning, right, of the joints. So this is something we need, and this is important for us. So we need that accuracy when positioning, and also we don't want the system to be very difficultly modeled, right? We want a very simple design model, mathematical model for the joint, so that later we can easily control the joint. So for us, accurate control of the system is very important. So let's see how we have addressed all these things, right? So what we propose is a simple design so that we can simply model with as a linear system, even if it is not. And then later with that linear system, we are proposing a specific type of control, which is called fractional order control. We will see what it is about. And so that the link can be controlled even in the case of loads on the tip, right? Imagine the situation in which the neck is free of load, but what if I put some loads on the neck? Imagine a different head, heavier, right? And the neck must, of course, support the new head of the robot. So let's see how to deal with these kind of things, right? So our first approach was to design this soft continuum, as you can see here, link, right? And this is actuated by 3 tendons. Initially, this is inelastic. The tendons are inelastic. We will see later how to improve that. And then the tendons are attached to some pulleys acted with motors. So it is as simple as I have a motor revolving, and then the tendon length is varying, right? So according to the variation of the tendon length, I have different inclinations and orientation of my joints. This is the thing, right? So of course, this is a non-linear system because of the non-linear characteristics of the continuum, depending on the material we use for it. And we want to simplify the model a lot. So what we have done is, okay, let's first analyze the configuration of the mechanism. We can identify simply with these 2 graphs, right? You can see there theta S as the orientation angle and theta P as the inclination angle. Imagine if you take the neck as a reference, we can incline, bend the neck, and also orientate in 360 degrees the neck. This is what we want to control. So we, of course, want to solve the kinematics problem here. So meaning, if I have a particular pose that I want to reach for my neck, what is the set of lengths for my tendons so that I can achieve that pose. This is the inverse kinematics that we solve next, right? So we can simply, easily find that relationship. You can see the graphs relating the particular pose, and for each of the pose in the 3D environment, the combination of tendon lengths, we need to achieve it. And this is because of the simple design of our neck. I have here, later you will see, this idea, first idea, has been transformed into this new idea, but you can see here that one of the simplicity brought by this design is that the curvature that you reach when bending is constant. Can you see? So it simplifies the mathematical model of this, the kinematics, inverse kinematics of this extremely. So it makes the system very ideal for later modeling and control. This is what we have achieved here. So, okay, now that we have the length of the tendon, this is simply translated into the rotational angle of my motor. And then the only thing I want to do is to control the motor so that I can control the pose of the link. As simple as that, right? And we experimentally test exciting the neck with different step inputs in inclination and measuring the final inclination of the tip with a sensor. We put a sensor here, we command an inclination bending, right? We measure the real bending, and we have a relationship between the output bending and the input bending. And this is, of course, we can look for more complicated models for that, but we have tried and adapted that to a very simple first-order linear system given by a transfer function, right? In which we can identify the gain of the system and the time constant of the system. And believe it or not, this complex, because of the material link, can be modeled dynamically as something as simple as this first-order transfer function. Right? This is what we have achieved thanks to a simple design in which the material, of course, provides flexibility, but at the same time, we can face, we will see later how, right, the simplification of the model. So assuming that this is the simple model we want to control, the next thing is to design a controller for it. For us, this is an important part, right? Because I repeat, we want to accurately position the link. So here the thing is that, of course, I agree that my model is having a lot of uncertainties because of the nonlinear nature of the material I am neglecting. I am considering this as having a linear behavior. I am going to face that. And this is where, and in fact, this is what I want. I want to demonstrate that even if I am linearizing and neglecting a lot of dynamics here, I can control it. I can face that from a robust control. So this is one thing. And the other thing is that, okay, this is a neck, and I want it to be loaded by different masses and see if I can face the control problem when this happens, right? So what we have done, since we have we need a robust control even in presence of loads at the tip, you will see that, right? We have tested how the load on the tip affects the model. And we have tested experimentally the neck, and we have demonstrated that the main parameter in the model is the gain of the transfer function. That gain k we have in the numerator of the transfer function. So eventually what we need is to reach a controller that provides robustness to gain changes, right? So if we can provide that, then it means that we could put different loads on the link, and the controller will face variations and keep it in the vertical position, if that is the constraint, to keep it vertical in a neck, right? Or in any other pose. So let's see. Of course, I'm not explaining here the controllers. This is another topic, but just to mention the three main characteristics or constraints we are providing with the controller. First of all, this is designed in the frequency domain. What we want is to adjust the overshoot of the response. Overshoot meaning the balance of it, right? If it is oscillating or not, we can adjust that with the controller, right? So we will design the performance for a particular overshoot, a percentage. And then also, of course, we want to tune the velocity of the system. I want the neck to bend faster or slower. This is something I can also tune, the speed of the system, right? And the third constraint is the robustness to loads at the tip, right? To gain variations of the transfer function, right? These three constraints are achieved thanks to the use of this controller that we proposed. You mentioned before the PD controller, right, in your previous talk. And in here, what we are using is the typical PID controller. People in control field know, right? But we are generalizing the orders of the integrator and the derivator. And then so that those orders can be fractional, non-integer, right? So for instance, with a simple PI controller with 3 parameters to tune KP, Ki, and alpha, we just simply can meet the 3 constraints, 3 parameters, 3 equations, and we can reach a solution. And this is what we have done in the frequency domain. So what does it mean? It means something very simple, that if I want my neck to bend like this over passing the final value, imagine 10%, this would be the maximum overshoot for whatever the load you put. Whatever. It can be faster or slower, but the overpass around the final value will be constant. This is the robustness we are looking for. Right? So, okay, here you can see an experiment in which we have loaded extremely the neck. This is 1 kilo, and the mass of the link is 14 grams, right? So you can see how with a robust control, we can face disturbances in which very heavily loaded, and also with a disturbance. We have the technician there, Raul, hitting and pushing the neck. You can see how it deforms, right? But very, very fast, it recovers the vertical position. And it is because of the, first of all, because of the design, but then because of the controller we are using. And this is tuned very easily as a linear system, and the controller is facing the variations and the non-linearities and mismatches we have introduced, or we have neglected mainly, right? So this is one thing. Okay, now we have improved the prototype because we wanted to use it, the link, as an arm. And this is the design I'm really showing you here. You can see the difference. Now the tendons are inside the structure, so the slackness is avoided, and it is more robust and secure, right? And you can see that the idea, the philosophy is exactly the same, but here we have patented the design, and this is because of the fact, I introduced that before, that we can bend having different blocking angles here to protect the extractor. So from the design, we can configure the design so that different angles, maximum angles, are achieved. Imagine that you are in a situation in which the arm needs to carry some loads, and you don't want the arm to bend a lot and break. In that case, you can configure the design so that these angles are forced, right? And you can protect the structure. This is behind the idea behind the patents, right? So using the same idea, the same type of control, here we can see how very accurately, believe me, this is very accurate, we can control the positioning of the arm with or without load. In the video at the bottom, you can see how for different loads we can very accurately also position the tip. This is the idea. So we are working on this, and now what we have thought is why not to scale this and use it as a gripper, right? These are now fingers, and in fact, these fingers are exactly like this piece here, and we want to achieve the grasping, facing the grasping with different surfaces. It is not the same that I grasp the ball using the edges, right, like this, or using the vertices, right? So for a very fine manipulation, maybe with the vertices, it would be better, but for a huge grasping, I would of course, prefer the edges so that the surface contact is bigger, right? We are demonstrating or studying how to demonstrate that according to the type of grasping required, I can rotate the finger and approach the object in different ways, right? Also with the blocking idea and limits. Well, we are still, this is the beginning of our project, but we are happy to see that we have some solutions already with possibilities, right? So this is also one of the approaches. And then, previous professor introduced the origami thing. Very happy to see this. This is also origami. This is the Kresslin pattern for the origami. But what we do here, this is the another gripper. I have it here. Later, if you want, we can make it function so that you can see this. So the idea is to have this solution here so that, as you can see in the video, the gripper adapts to the object. I'm not really acting on the fingers, but on the origami structure so that it adapts. So imagine that you are like manipulating a sponge, right? The dynamics of the formation here couples with the dynamics of the formation here. So this is the idea, to make it more adaptable and safer for the grasping. This is the idea. We have also installed the gripper in the robot Iago, which is a manipulator, right? So later, if you want, we can show you. And this is maybe a simple proof of concept, I agree, but the idea of it is to make the gripper to build it with self-healing materials. I don't know if you have heard of it, but the idea is, why not to build the origami with this material that I have here. This is in the envelope because apparently you cannot directly touch it. You have to manipulate it with some gloves, right? But the idea is, what if we manage to create the origami as an artificial muscle? We can also introduce it into water. I mean, there is no limitation for us because of the water environment. But the idea, what if it breaks, right, because of a fissure or whatever? So the idea, it can self-heal, which is the amazing particularity of this material. You can see in the video that this happens, right? After certain cycles, I don't know if we can repeat it or, oh, I will do it here, from here. Yes, you can see, oh, sorry. Let's see, running. Now running. Okay, you can see that in the edge, it breaks, right? So if the break is not that big, during a certain time, maybe some minutes or maybe hours, it depends on the material we use for the structure, right? It can recover itself, right? But if not, if it is a huge break, as you can see there, maybe we have to add extra material, heat it in the oven at 60 degrees, in this case, and recover the module. So we can use and reuse the module as many times as we need, because their functionalities are totally, fully recovered. Right? This is the idea. And we are working on these self-healing materials too. And also having, making use of these characteristics of the material, we have developed a connector. This is a connector made of self-healing materials again, and with temperature we can connect and disconnect the modules without the need of mechanical elements like, attachments or whatever. Very easily and in a controlled way, using temperature control, we can attach and deattach the modules. So easy to plug and play, let's say, and heal. So this is also a part of our research. So far, what we have addressed is some solutions, right, in which the material is part of the structure of the robot. But also we can address sensor parts, sensor systems, and actuator systems. I don't know if you're familiar with probably you are, with shape memory alloys. These kinds of materials are like amazing because they have a property, when you heat them, they contract, and when temperature recovers, right, they elongate again to the original form. So with these kind of magical wires, we can also, we are working on it, we have replaced the tendons, inelastic tendons of the previous neck. And here we have tested what happens if now the tendons are SMA-based actuators, right? So heating them and cooling them, we can change the lengths of the tendons, and then we can provide some movements to the neck. We agreed that the actuation, because with temperature, you know, it happens, the velocity of the actuator is reduced, is limited, but in some applications, we don't need the actuator to be that fast. And then the next solution is one case. You can see how this is an elbow exoskeleton in which the SMA, the wire, is here in the elbow, enrolled, right, in a pulley. So with temperature, controlling currents inside the tendons, we can make the arm flex and extend, right? So with applying current, we have the flexion, and then when the current is cut over, then the arm recovers the original extension. So replacing motors, right, by these kind of actuators, what we find is that the system is very, very light, and there is no noise at all in the actuation, which is a good thing for people suffering from, for instance, an ictus or with maybe depression or anxiety. In this case, we better if we avoid any type of sounds around, right? So this is one of the applications we have addressed, apart from using them as tendons for the necks and the arms we are developing. And also sensors, right? We work with a variety of sensors like this one. You can see here a lot of samples, right? We are just researching on many different types of them, polymeric matrix that we can also let's say, reconfigure using also other materials inside, right? So the thing is that since we are using bendable surfaces, right, why not to attach the sensors to the bendable surfaces and measure directly what happens there directly with a very flexible solution. And not just these materials, but also, well, I don't have it here, but the last one you can see here, this is carbon nanofibers tendons, right, sorry, sensors, in which we can this is in fact the next, no, it's not here, sorry. But we can measure very easily how the electrical characteristics of the material changes with the deformation. So this is something we are also researching on. And as an just to finish, more than these cases in which we are working, now we are very, very happy to see that we have an opportunity in the development of this cervical orthesis, in which what we want is to, first of all, create an orthesis very soft so that it can adapt to any neck, healthy people or maybe people with movement disabilities, right? And we want to integrate inside these type of sensors and also these type of tendons, SMA tendons actuators, so that finally what we want, what we have is a platform able to not only monitor the positioning of any neck, right, but also to be able to act on the positioning of the neck for cases in which the patient maybe cannot move the neck or need the neck to be blocked up at a particular position, right? So we are just starting the project, but we are confident that we can get a solution in which we can integrate these intelligent soft materials as actuators and sensors for a more portable, easy to wear, and also cheap solution for this kind of people needing these kind of devices, right? And well, this is all. Of course, there are some projects behind funding this research, thanks to the ministry mainly for all the opportunity given to us, right? And of course, it is possible because we have a great group behind. Lisbeth, for instance, is here, one of our now doctors that have developed, she developed the gripper and many other things that I have shown you today. So, well, thank you to all of them. And thank you for attending the conference. Thank you very much.
Okay, so thank you very much for the inspiring presentation. So now we have some time for questions. I have many, but okay, there we have one. Marwa and Eliseo, any one and then the other one.
Thank you so much, Concha. Very interesting presentation.
Thank you.
Just a quick question. I'm interested about the 3D printing of the TBU, the conductive TBU. I'm not sure if you read the problem of the conductivity. If you have the conductive TBU and the 3D printing, the conductivity sometimes is affected. So,
yeah, it is a huge problem for us. In fact, what we collaborate with AIMPLAS, which is the Plastic Institute in Valencia. So they are the ones leading with these kind of things and problems, also IMDEA materials. So we have as partners these people very in the topic, right? So they somehow tell us how to face these kind of problems, because of course conductivity, the noise in the measurements, this is something difficult to face, right? But well, how you weld the connectors, how you filter the signals, this is something we are, and Elizabeth, she's here, and she's the one that, who has faced all those problems. But eventually we have reached good solutions for that, and let's say that the material is manageable as a sensor, somehow giving us repetitive measurements and showing possibilities to be used as a robust sensor for the applications. But it depends a lot on the materials we are using, and well, and yeah, there are many things affecting, right, the robustness of the material as sensor. This is of course the main one, I would say. Thank you, very interesting question.
So, following one.
Okay, good presentation, thank you. My question is more related how you're handling with the non-linearity of the SMEA and hysteresis for the material, and if they are suitable from underwater robots for sure.
Yeah. Well, I totally agree. This is, as you may imagine, very non-linear. We had hysteresis there. So what we use is a controller, specific control, to avoid that, to manage these kind of things, non-linear control for that. And if you are interested later, I can show you some papers in which we deal the problem specifically. But we can manage, even with fractional order controllers, we can, in the linear part, we can control it like this, and we can compensate the non-linear part with a bilinear controller. We will show you later if you are interested. And regarding the fact that this is underwater, well, we are not experienced this kind of applications so far, but I must tell you that I don't know if you know octopus. This is an octopus developed in Pisa by a research group there. This is one of the main soft robots as a reference when we think of soft robotics. And it is acted by SMAs, and what they do is to introduce the octopus in the water, and the actuations, of course, is outside the water, right? But since for SMA, what we need is a simple power control cage, we can protect that for water, environment, and we don't think this is a real problem, because the SMA would be inside a capsule, and also introduced into the material of the robot, so it is protected by the shape, by the body of the robot.
Okay. Well, maybe in the meantime, I just got an idea now. I just want to share.
Yeah, please.
Because in the end, somehow you are controlling like kinematics.
Yes.
But what about material properties? So I was thinking, just to link with underwater, that it will be ideal if you put all these systems with there's something called magnetorheological fluid.
Yes.
Where essentially it's perfect because it's incompressible, so it can go underwater, keeping the pressure. So in the end, by controlling the current for generating the magnetic field, you can control and adapt the stiffness, right? So
yeah.
I was thinking about these first ideas you were showing, right? Doing like that and then with the damping. So I was thinking that maybe this is kind of ideal, right, for this kind of applications, because you are directly controlling the viscosity. So
yes, it is, and in fact, this was one of the first proposals we had. But we, as a first step, we decided to use a simple continuum material as a whole, easy to bend with tendons, right? And let's see later if we can improve using these kind of approaches you're offering us, right? But of course, this is something we considered. And I totally agree that in here, the nonlinearities of the material, how they affect the approach, because they affect. The thing here is that after several, I must say, a lot of them, cycles of performances, right, of the joints, we can observe, maybe not physically, but visually, but of course the material somehow is affected, right, and deteriorates, right? So it happens that when it recovers the original position, it's not exactly the zero position, right? You can see that because of the nonlinearity of the material, something happens in every cycle, right? This is why we are introducing now artificial intelligence.
Okay.
Because in our control, we want to avoid data. Meaning we need the analytical model for it, because we are happy with having the analytical model, right? And also from the model we can design very easily all our controllers, right? And it works. But if you want after certain cycles, right, when something happens, because robustness here is for, okay, I have the nominal system and slight variations around the nominal system, not all type of variations, right? So if something happens in the structure leading to a different dynamics, then I would have to retune again the controller, recalculate the model and retune the controller. With artificial intelligence, we can do that in time, online, right? And we can face the problems. And we are now testing these approaches on the real necks and arms.
Because when you are thinking about non-linear, you're just thinking in elastic terms, because also you have non-linear elastic terms there, viscoelasticity and all these things.
Yeah.
So you are also...
Yeah, everything.
Okay.
So, but following your idea, we wanted just to have a very simple design. Let's see if with a simple assumption of the model and what is inside here, which is not that simple, right? We can face at least a first control approach, right? Very accurately, or at least we can position the joints accurately for accurate grasping or positioning of their joint, and we are quite happy, right?
Okay.
I don't think we need to make it more complex if somehow it works for certain applications.
Great. Niels?
Thank you very much for a very nice presentation.
Thank you.
A lot of interesting examples, and coming from structural optimization, I'm sure you will see that from tomorrow morning, there's plenty of room for collaboration. But I have a quite practical question regarding the actuation of the arm. So, and this is sort of tied to the question from the gentleman down there. Is it possible to actuate quickly enough to actually make useful hand movements and arm movements with these SMAs?
Not that accurate, I agree. For that case, because it's a nonlinear material, it takes time to control it. Sometimes if the precision the precision requested is very accurate, maybe it's not the best actuator, right? For the neck, we have demonstrated that we can accurately act, but we haven't yet integrated these kind of tendons in the arm. So this is something we still have to do and see how it works. Because now with the gravity, and the nonlinearities of the material, let's see how it works. I assume that we will have some problems there, right?
So related to underwater robots, it would be a slow swimmer.
Yes.
And maybe.
Yeah, of course, for these kind of applications. But since we want to integrate that into the humanoids, so that we can provide an accurate grasping and manipulation, we still have some limits for some type of actuation.
Any other question from the audience? Okay, Fabrizio.
Very nice talk.
Thank you.
I was quite actually, taken aback by how efficient the fractional order derivative control system you are using. Is there any limit using fractional order control in terms of system and materials? Because I assume that you need to guarantee some consistency of higher order derivatives to make really fractional order control work.
The idea, if you have a transfer function to control, right? As a first side, we could say that the fractional order, you can find a fractional order controller for that transfer function to be controlled, whatever the specification. Meaning, even if the phase margin, for instance, you want to get is very high, because of the freedom of selecting the orders of the derivative of the integral, you can get that number, for instance, 2.3, allowing you to reach that particular frequency specification. I don't know if I am answering your question.
So you could use a fractional order control on any type of system, you say?
As far as this is linear. With this technique, the idea is that the system is linear.
Thank you.
And at some point, I guess you
But
can
of
linearize.
course, you can also use it for nonlinear systems. But with these tuning techniques I am proposing, the system is linear. Mm-hmm.
And if this is not linear, you can just like linearize
Linearize by
part
zones, and that's
right?
it. That's it. This is what we do, in fact.
Yeah.
Or use adaptive control. So for every different region you are approaching with your joint, you recalculate the model and retune the controller parameters.
Mm-hmm.
And it is working perfectly well. But you need to linearize somehow and recalculate the linear behavior so that you can retune the controller later. If you want to do it also with a small computational cost, which is also important.
Great.
Okay.
Any other question? We already
Very
have a lot.
interesting
But
questions. Thank you very much.
okay, so let's thanks again.
Thank you.
Okay, so now we have our last speaker before the break. This is Professor Mokarram Hossain from Swansea University. And Mokarram, I hope now you are well in Spain because yesterday... Okay, so it's my pleasure to present Mokarram. Actually, I met Mokarram from how many years? I don't know. We started collaborating online in COVID. So Mokarram is Associate Professor at Thinkevik Institute for Modeling, Data and Artificial Intelligence at Swansea University. So his interests lie in the broad and interdisciplinary areas of soft polymeric and multifunctional active materials, ranging from material synthesis, experimental studies, and computational modeling. Many works on magneto-active and electro-active. And he has published more than 120 papers in journals on materials, mechanics, and computations. And Mokarram is going to tell us today about recent advances in electroactive materials from different dimensions, actuators, sensors, and especially energy harvesters, right? So please.
Yeah. Thanks a lot, Daniel. Thanks a lot, Daniel, for the invitations and the introduction. Nice introduction. As Daniel already mentioned, I will talk about the so-called electroactive polymers. So you can understand this is basically a polymeric material, a very soft material that can be used as actuators, sensors, and energy harvesters. Since already Concepción and other people already talk about sensors and actuators, I will mainly focus on energy harvesters, and hopefully nobody in this session will cover this area, how we can use soft materials or rubber-like materials to produce energy, the clean and green energy, which is the major issue nowadays, right? So what is electroactive polymers or EAPs? So electroactive polymers is, as I said, polymers, but now you are applying the electric field or electric actuations
and you are getting something, for example, mechanical actuations, right? So this is the video that I produced a couple of years ago, and this is a very transparent, the transparent polymer, and then the black actually the grease, carbon conductive grease, or the so-called electrode, right? So if you paint the polymeric material in the top and bottom, and then if you attach with the electric connections, then basically what you are doing through this electric connection at the top, you can see you are charging positive and negative, and due to the attraction of the opposite chairs, you will get the contraction along the thickness and expansion in the longitudinal directions. That means you are applying the electric field or electric voltage, and you are getting the mechanical actuation. So this is the actuator mode. So today I will not concentrate on this, but I will go to another area, that is how we can use this electroactive polymer to generate energy from some ambient motions, for example, the wave, right? And okay, so we have huge wave resources, at least in Europe or UK, surrounded by this wave energy. So how we can use this wave motion to generate energy through the electroactive polymer? The principle is very simple, like the actuator. So the figure 1, you have the polymeric material of the thin sheet, thin membrane. You put the electrode top and bottom, and then due to the wave motions, somehow you can think that wave will force the polymeric material to deform, right? And then if you put some charge, positive and negative, that we call it bias voltage, then you are getting a different type of capacitance. You have the position A and position B. You can see, if you look into the equation of the capacitance, now you have very thin, right, compared to the first case, and you have the large area. That means capacitance is very high. Now, wave disappears, the polymer is largely elastic materials, more or less, it will come back, and then you will get the minimum capacitance, and this difference of the capacitance you can harvest as the energy, right? More or less, this is the cycle. And the next wave will come, and then, so I was lucky, my first PhD student was supported by this company, so I would like to show you a video, and this very practical experience. Okay. Hopefully you can see. If not, you will see. No? Okay. It doesn't come? Yes.
Out to sea, safely beneath the ocean's waves, sits M-Wave.
Okay, so
Bombora's pioneering patented technology harnesses
okay, so here you can see this is the flexible material device that put underwater, and due to the wave, this flexible material,
flexible rubber cells, each 15 meters in length, are mounted to a concrete foundation structure arranged to
from the top.
No, you have to. No. This. No. Okay. Oh. So you can see. So this is the elastomeric material filled with air, and due to the incoming wave, this will inflate and deflate. And since it is filled with air, and the air will pass in some device that is connected to the generator and motor that will create the energy. So here, this is the typical application of the flexible device using the rubber-like material to generate energy. But I said, okay, now we are interested to see, now we are not interested to make many parts, for example, the so-called
makes it rapidly scalable.
Yeah, so this is the device. You have the flexible membrane. So it's called primary mover that separate the water with the main device, and then you have other components and so on. Now, our next target is, can we use this elastomeric material as the generator? So I don't have any generator separately, right? So this polymeric material will be stressable according to the principle that I have shown you, and it will generate the energy. Yes, we can. Let me show you another device. So that is called DAG, dielectric elastomer generator, right? So now the simplicity of this, we don't need extra generator, extra device, and so on. The rubber-like material will be stressable, and that will create the energy. So the problem here, in the previous slide, you can see that it is the stressing and de-stressing, right? And how many cycles it will survive? That's the main question. Maybe millions, couple of millions. That means after few months or few years, you have to change the device, right? So the fatigue issue is the major issue for this rubber-like material as a generator. So people say, okay, now can we think about it in a different way? So instead of this thin sheet, can we replace the material and put as a dielectric liquid, right? So this is very recent development, and then you can see now we have this very simple device. Now we have the electrode in the top and bottom that is filled by a fluid. And a fluid is basically has unlimited number of cycles. So you can go and fluid will come back and you can continue. So there is no dielectric breakdown compared to the elastomeric material. And then you can consider the self-healing material or self-healing layer, right? And the principle is the same. You have the electrode in top and bottom, and then that could be flexible electrode or that could be rigid electrode. Rigid electrode means you have like this, and you can deform. You don't need to deform the electrode. Just change the volume, and that will change the capacitance. So, and that is called dielectric fluid generator. So now we have two types of generator, dielectric elastomeric generator and dielectric fluid generator. But for the both case, the fatigue is a major issue. So either you will covered by the electrode or elastomeric layer in the top and bottom, and these materials are fatigue prone. So next slide, I will concentrate mainly on the fatigue issue. But before that, we can also make this flexible material as a small device. So let's say a small generator, and then we can connect to make it large generator. So that means this is a part of the so-called metamaterial community, right? So either you can use as a dielectric fluid generator or dielectric elastomer generator, and you can make a big, so this is hexagonal device, and you can make it as a dielectric elastomer. You can paint the top layer and bottom layer, and due to the wave, it will stressable and come back, and that will generate the energy. So, and then this small device, you can connect to make a big device, and so on. So how it looks, so in the top, you can see the principle. Either it will be stressable or just flexible. That will change the capacitance. And then the small components that could be several hundred micron, right? Or several centimeter. And then you assemble, and that could be a big system of generating energy. So this is the recent development. I was lucky I was working with a company that was funding a PhD student in this area. So another area is the flexible sensor. I think you already, Concepción, talk a lot, so I will not go into details. But here, one of the major questions that she has shown, like this, right? So how your sensor will act when you have millions of cycles, right? Does it survive, or the prediction is accurate during the cycle, right? So my main focus is to understand the capacitance or the resistive behavior in millions of cycles. So if you want to use this flexible sensor in dynamical case, then you need to understand that after millions of cycles, my sensor works as it is, right? It can predict as the virgin case. So, okay, so let me show you one sensor that one of our PhD students just prepared. And here, this is the sensor. I think Jesus and Rogelio have recently seen. Then you can see if you deform it, and you can see the capacitance and resistivity changing. So this is the work of one student, but my another student is doing how to design this conductive path, right? So you can create different metamaterials and so on. So, and then you can put the top layer and bottom layer, And you can just, she joined recently. This is the earliest course. But my main target is to see how your sensor is more or less insensitive with the cycle, right? Either it could be resistive sensor or conductive sensor, but I want to see that this sensor property does not vary over time, over cycle. Okay, so I'm not going into details. Let me go to the area that is very, very important for the company. How many years, how many cycles this cell or metamaterial or the DAG or DFG or the flexible sensor will survive, right? So if you look into the applications, it's not only about the energy harvester. It's not only about in flexible sensor, skin mounted sensors for the training and sport purpose, right? So you have millions of cycles. But interesting thing is you cannot provide the data with the uniaxial fatigue. You said, oh, I take a dog bone sample and go to the machine, instrument machine, I do this. No, it will not work. Because you are working at least in a membrane type shape and you are getting multi-axial deformation. So I was lucky to get some funding a couple of years ago to develop a customized system that can do multi-axial fatigue test. And this is the machine. You can see this is really, really customized machine for sub-material. And this is the machine. And you can put the sample underwater. So this is the DIC underwater. So you can track the deformation underwater. And the water temperature you can change if you want. So you can go up to 60 or 80 degrees centigrade temperature. So we have the recirculating system. And it can keep the temperature constant. But most important thing is you can deform the sample up to 500% deformation, okay? And sensor is very, very sensitive. So we have 5 or 10 Newton to 2 kilonewton load cell. So it's a large range. And you can test biological tissue or hydrogel and so on. And we have different type of waveforms, so square, triangle, sawtooth, and so on, and sinusoidal. So you can use different type of frequency and the waveform as well during your fatigue test. So this is the close look. This is the biaxial sample, the cruciform sample with the DIC, and you can see underwater. Okay, so the same machine, if somebody said, okay, I'm interested to see only uniaxial data underwater. Okay, fine, I can do that. So I will just deactivate the other axis. So both axes are completely independent. There is no connection of axis X with axis Y. Okay, so you can do, for example, 3 dog bone sample at a time underwater without water, or then we modify. So, okay, if only 3 and that takes 9 months, no way. So what we do, we said, okay, we change the system. Now we can test up to 24 samples, and 12 samples on one axis and 12 samples in another axis, right? And then you can do the averaging very quickly. And then on the top, we have the DIC, and the DIC can monitor when and at what time, which cycle, and what sample breaks. So we are done with uniaxial, very good. So far, so good. Then I got another funding, so they said, can you enhance the fatigue life? Okay, and what are the ways? There are plenty of discussion in the literature. If we incorporate some so-called 1D material like carbon nanotube or 2D material like graphene, then people say the fatigue life will increase. But we found it's a stupid innovation because what people did, people cut the sample and they do the fatigue test, and they found that this crack does not propagate because there is some barrier. Fine, but what is happening if you take a virgin sample and do the fatigue? I will show you. Okay, so before that, we prepared the sample in our lab by 2 ways. So we mix the CNT or carbon black or other pillar in the liquid phase and the solid phase, right? Liquid phase means we dissolve the, for example, natural rubber or other polymer and put the pillar, and in the solid case, we have the powder and mix up with the gum, and that makes the so-called dry mixing, okay? And then we see what is happening. So this is the uniaxial fatigue. And you see, due to the incorporation of the CNT, there are plenty of cracks at the beginning. And these people do not consider the virgin sample. They took some sample and they cut the sample. So that means you can say that the crack propagation approach and then the so-called other approach, crack initiation approach, is the same. It will give you the same fatigue life for unfilled polymer, but not for filled polymer. Okay? So we found that for CNT filled elastomer, the fatigue life is significantly less if you take with the virgin sample. So here you can see. So we did two types of fatigue test. One is the submerge. So we put the sample under water, and we did this fatigue test with the virgin sample. That means it took 6 months to get one set of data, right? And you see that, or 3 months, 6 months sometimes, and you see for the dry case, the dry means I'm pulling it up to 100% in dry condition, no water, and I'm putting this sample up to 100% in wet environment. That means with water, right? And I found that the submerged condition fatigue is much more high than the dry condition. Please keep in mind, this is not of the synthesis. I do two types of synthesis. One is dry and one is wet. I'm not talking about the synthesis technique. I'm talking about the testing condition. One is dry, one is wet. If it's wet, then you are getting higher fatigue life. That means if you do the fatigue in the sea, you will get higher fatigue. The reason is, during the fatigue life cycle, there is significant amount of heat generation, okay, in dry case, and that decreases the fatigue life, which is not the case when your sample is underwater. And what is happening? If you take the sample that is produced from dry synthesis technique or wet synthesis technique, then you see, okay, for dry, you get the higher fatigue life, and the wet, you are getting lower fatigue life. The reason is, okay, so reason is, then we did some microscopic analysis, and we found that during the synthesis with the dry condition, when you're mixing with the liquid, there is significant amount of bubbles formation inside the sample. And that makes the fatigue life really, really less compared to the dry condition. Okay, so this is, the left side is the dry condition, and the right side is the wet condition. So you can see there are some big bubbles, and when you test the sample with, test the fatigue test with the virgin sample, there are immediate cracks due to these big bubbles. Okay, so we are happy with the work that we did with the uniaxial fatigue, with different synthesis technique, dry fatigue, wet fatigue, and so on. But please keep in mind, why you are interested to do this? Because of this web company, they said, oh, we don't know anything about the fatigue life. Can you do the test? Before taking this device or the technique to the next level, please give us some fatigue data. Okay, and this is the same thing for the flexible sensor if you want to put in the dynamic condition, right? So you need to see whether the resistivity or conductivity is varying over the cycle. So, okay, we also did some biaxial, now I'm moving to biaxial test. Biaxial, so here, this is the cruciform sample underwater, and it took a lot of time to understand the speckle pattern and the DIC underwater. And you can see, we can nicely track the contour, the deformation contour underwater. Or if you, if you could take the square sample, it can also nicely track the speckle pattern underwater. So this is not dynamic test. This is not about cyclic test, okay? Then I said, okay, let's do some biaxial fatigue test. Please keep in mind, this is biaxial means biaxial. It's not you have the inflation bubble, no. I'm not doing, because there is axisymmetric equibiaxial, right? We're interested to do non-equibiaxial. That means you can apply the force in x-axis one type and y-axis completely another type, right? This is the case if you look into the wave device that I have shown you, it's a non-equibiaxial. So this is at first we did the equibiaxial to see where the crack form, right? And when I was talking to different people about the biaxial fatigue, they said, oh, you can't do, because the fatigue will happen in the gripping section, right? And this is the case. So we found the fatigue start or the crack start at the gripping section, the diagonally, either in some of the gripping section. Then one way is to make the gripper, I'm not sure I have this photo or not, but I did not put it here. So then we put some glue, and then we make the S a little bit thicker, but still problem is there. Then we move to the so-called the cruciform sample. And here, what we did, after a lot of trial and error, it took a lot of time to understand that, okay, if we do the S sections a little bit thicker compared to the middle section, because our focus is the middle section, right? And what is happening. So this survives after millions of cycles. But here, what we did, we glue the S section compared to the middle section. But we don't want to glue, because sometimes the glue somehow breaks, right? Then what we did, okay. So there is another approach we found in the literature. People say if you make the sample like this way and you make some longitudinal, or some, I should say, bar type thicker S, then the gripping will be nice. But we do not test. Here we use just thick edges compared to the middle section, and it survives millions of cycles. And then we tried a little bit more, so-called non-equiaxial. That means we pull the sample 100% in one direction and 10% in another directions. What is happening? So here, so both sides, this side we have 10%, and that side we have 50%, I think. And here, this is not glue sample. It's one sample. So we cast the sample as only one sample, and the middle section is thinner compared to the other section. So now, our DIC will only concentrate on the middle section. And this survives. That means we don't have any failure from the S. If failure happens, it should be in the middle sections. So that works fine. So far, we did, I think, 9 million cycles so far. So this is about biaxial, non-equiaxial fatigue so far. And again, please keep in mind why I'm concentrating on the non-equiaxial, because of the application, either in web device or if you have the sensor, skin mounting sensor, or are experiencing non-equiaxial deformation, right? So you cannot take into account only the fatigue life from uniaxial dog bone sample and you can play. No, it's not possible. Okay, so now I will quickly move to actuator, how we can use the electro-active polymer as an actuator. But again, my colleague, Rogelio, will talk about more about electro-active polymer, hopefully tomorrow. But I'm not going into details about modeling of electro-active polymer. I will show you some more results, experimental results of electro-active polymer as actuator, okay? And think about temperature. Think about Madrid condition and think about Swansea condition, right? In winter and in summer. Swansea is now minus and Madrid is 18. And you are sending a robot to Swansea or to Swansea to Madrid, and you're saying, okay, it will function well. No, it will not work. You are worried about viscosity. I'm worried about temperature as well, right? So I was working with a polymer that is called VSB. It's a commercially available polymer for 3M. And I did my postdoc in Germany, and I did the test during summer, and I was writing the paper in winter. And then, I found that I need one data. Then I asked my student worker, I said, can you do more tests? Then he came up with some new results that is completely different than what I said. What? I said, did you test? I mean, it's a very good student. I can rely. But this is not Dr. Hossain. This is the data I produced. Believe me. I said, okay, let's go to the lab together. And then I found that it has more or less double stress than the summer case. That means if you have less temperature, right, or high temperature, it's 5 degrees centigrade temperature, increase the stress response almost double, right? So you are talking about room temperature. Room temperature in winter and room temperature in summer is not the same, right? Unless you maintain the temperature constantly, right? So 5 degrees centigrade temperature gives me almost double. So What is the novelty here? We published a lot of papers since 2015, in the last 9 years. So what we did, in the left side, you can see, now we have a device that can do electromechanical actuations. That means you can deform the sample. You are applying the mechanical force, as well as you are applying the electric voltage. That means simultaneously you are applying the electromechanical field. But then we put inside a chamber, where you can control the temperature up to 110 or 120. So let me show you the result. So typically, this polymeric material is viscoelastic, except 1 or 2% polymeric material. 95%, even someone tell you, that, I use a hyperelastic model and I use, it's nonsense. None of the polymeric material are hyperelastic. It's viscoelastic, 99% or 95% at least. So that means it is a dependency, it has relaxation, and so on. So you can see the polymer that we have been using, the VSB, is a commercial polymer. And then you see rate sensitivity, right? Or different strain rate, and you are getting. And then if you do the relaxation test, it has significant amount of relaxation if you pull the sample and you wait for a couple of minutes, and then you will find the relaxed state. Okay, so this is about mechanical test. Then what will happen if you do electromechanical test, right? Electromechanical test means you are pulling the sample. At the same time, you are applying the electric voltage. Since you are applying the electric voltage along the thickness direction, the polymer will expand in this direction. So in the same direction, you are applying the mechanical field. That means you are getting a less response compared to the mechanical case. So this is the case. So if you increase, this is the temperature. I'm sorry. This is only a fixed strain rate, but with temperature. Look at here. So you are getting a temperature, I cannot remember, it's 20 degrees centigrade temperature, this 0.8, and then when you have 40 degrees centigrade temperature, it's almost double, right? 0.8 to 0.36. That means the temperature increase, you are getting less force or less stress. So what is happening? The same thing, if you apply the temperature during your relaxation test, and you are getting the less response if you increase the temperature, and so on. And so from there, you can extract the so-called equilibrium stress, and then you can plot. Then you can clearly see that the temperature has a significant influence on your viscous response, as well as your hyperelastic response or equilibrium response, both. And then, in the same chamber, we apply the electric field. And in the left side, you can see, as I mentioned already, that if you have the deformation in the longitudinal direction and you apply the electric voltage in the thickness directions, that means you are releasing the force. And that force you can clearly see in the top. That means if you have a 0, that means no electrical force. And if you increase the electrical force or higher voltage, then you will get a reduced deformation because you are releasing the force in the perpendicular directions. So, and then finally, we combine mechanical, temperature, and electric voltage, and this is the experimental data. Good news is I also did modeling of this, but I don't want to present here because my time is out. Thanks a lot. Okay.
Okay, thank you very much, Mokarram. Okay, questions? Yeah.
Thank you. Thank you, Mokarram. It's really super interesting presentation. I have a couple of questions for you. The first one, maybe the easiest, the DIC. I use DIC for the soft material, submersion water. And I was really impressed to see the full strain stress field. And I don't know what speckle did you use for the soft material, because it's a challenge. Yes. And I'm not sure if you do fatigue tests. I assume you didn't do that for DIC.
So
right?
far, for all the tests with the DIC and a speckle pattern, we did only for
what did you
couple
use?
of cycle, not fatigue cycle.
Yeah.
So the speckle pattern, very good question. That means you failed, right? And we are successful. That's thanks, Lord. Oh, sorry, not to undermine. That means you know there is a challenge. Okay. Oh, can you please? No, I cannot show here. So I want to. Yes. So here, actually, if you see, the quality is quite good. Am I right? I have more data where we did the crack propagation up to 200%, and the company is so impressed. They said, "Okay, we want to extend your contract." So the reason is we did the so-called more regular pattern, so the brush, and then we spray. So we combine both.
Because when you move it, the mechanical properties of speckles
Different,
change.
yes, significantly.
And you
Yes.
need to track
Yeah. So that means the way is we combine both approach. This speckle we paint, right, and then we brush.
And how you protect it from the water.
Oh, this more or less it is. We try with different coating system, and one coating system survives. It does not disappear with water. Yes.
Okay.
There are something commercially available.
Okay.
You need to play with.
The second question I find it's interesting about the fatigue when you design this structure. I think if you go slide 17, I'm not sure if it's 17 or 16. The one with the shoe, the Adidas 4D shoe and...
Motivation, you mean?
No, the Adidas 4D. Yes, this one. Yes.
Yeah.
So this is a very interesting one, but because the one that with the white and red, this using two different material to increase toughness and delay damage. And I think this is completely different what you have been doing.
Okay, so here I want to...
I still didn't ask a question. Maybe I have to continue my question, sir.
Yes, please.
So the trick is that from your work, I understand there's two different techniques you can achieve the fatigue material structure that has fatigue resistant. So here, this is two different materials, soft and hard, and that's what happens in nature. Like some animals, you have soft and hard, and you play with geometry to increase toughness and delay damage.
Yes.
So it's different between what you show and this image. Yeah.
Okay, so here, actually, I want to motivate you why I'm interested to do the biaxial fatigue or non-equiaxial fatigue.
Yeah.
Because for this approach, the paper that Suo group and other people are doing, you are taking and we are pulling in one direction, but you don't know there is a chain in the other direction. So that means you are giving me data, taking the stressability in one direction, but you have entanglement in the cross-link in other direction, and you completely forget. And you don't consider the influence in other direction. So I'm giving you the motivation why I'm interested to do biaxial fatigue. The reason is this. So we have the cross-link, and then you have to take into account, especially if you want to increase the fatigue life through this design. My approach is not to design. I'm taking from market. I'm talking from literature. But my approach is why.
But I'm interested in your opinion about that, because what you mentioned next slide, it's not exactly the same approach. You're talking in more the material level, here in more macroscopic level. So they use soft and hard material. Do you see that there's differences if you want to design a structure that can delay damage, and we don't use self-healing?
Yes, we are doing
structure.
Yes, we are doing right now. So again, I'm not designing new synthesis. I'm taking. I believe that what Suo group did, fine, but I want to test what is happening with the biaxial fatigue.
Very thanks for the presentation. Was really amazing. Seems like a animal briefing or something like that. I think it's a really big project. I was thinking using, maybe if you're thinking to miniaturize the system in order to, how to say, use for drones underwater and, how to say, improve the autonomy of some kind of robotic things, because I don't know if it can be used in small devices. Yeah, the autonomous, that means whether we can use as a sensor and the energy harvester simultaneously, for example, right? Yeah, so that I do not do in that direction, so to be honest with you. So here, I'm just focusing how the soft device or the architecture can give me some energy. But you were right, we can make more autonomous, and this is one of the reason the company that I have shown you, they want to make this flexible device as a self-sensing as well, so that can give you the crack propagations, because they're underwater and you don't have any the monitoring mechanism, right? So if you develop some sensing mechanism, and that can give the warning, oh, your flexible device is about to fail, so hey, please do something. So yeah, of course, this is one, and then as well as we can use as an actuator. So this is the area in future we need to focus. The same thing we can use actuator, sensor, and energy harvester. Why not? Yes, we are moving in that direction.
Okay, any other question? Okay, here Fabrizio. Maybe in the meantime, a quick question. So you saw that under virgin conditions, with the conductive particles, they behave much worse, right? So my question is, did you optimize a vacuum system to extract the bubbles and also coating to get? So do you think this is something that's going to happen just because of the sharp, contrast in stiffness, or this is more about the adhesion that you can get from the...
Very, very good question. Thanks a lot, Daniel. So 2 things. One is, if I want to make this as a sensor, then we found that the weight technique is better. Because then you can disperse the CNT nicely. And then when you stress it, you will have the channeling very easily compared to the weakly dispersed. So what is your application? If you said, okay, I want to make sensor, and in that case, fatigue life is maybe not my first priority. My first priority is the high sensitivity, right? So in that case, I would prefer to go with the weight method. But if you want to make it as a device for energy harvester, what the company is struggling to make is a large-scale device. The large-scale membrane is, for example, 6 meter by 6 meter, right? And in that case, this weight method is not the ideal for them. They have a huge amount of material, and then they throw the powder, and they mix it, and make the sheet. So in that case, they want to say, okay, can you tell us what is the fatigue life if you go on weight method and dry method? Then I said, okay, dry method, what you are doing is fine. But it depends on application.
Okay, really good point. Fabrizio?
Mokarram, really fascinating talk. I have two questions, but probably I will ask one because the other one next time. But just quick, regarding really the natural rubber and the carbon nanotubes, just to clarify the manufacturing process, did you first really made the compounding with the screwdriver and then?
Yes.
Okay.
Yes, we did. Yes. Yeah,
Okay,
the professional way, we did in TARC in Huddersfield. I mean, they have the best facility in the world.
Okay, so you have the time for the second question in that case. Well, obviously, I was very interested on your cellular device, and I find also very interesting also the type of work that you try really to architect really the sort of the conductive circuit.
Yes, that's my students just started. She said, I want to say, okay, go ahead, whatever you like.
You did well.
Yes.
So I just have a question. In the sort of design of the single, if you want, units that you showed before, you see that in essence, every unit has got to really inlet and outlets in order really to control the fluid.
Yes.
Okay. In the demonstrator that you show, you have really several cells, and so there is a relatively size-scale effect when you inject effectively the liquid there. Is your intention really to look at more size-scale effects when you increase the number of cells, or do you want to really to keep that kind of scale?
Okay, so I cannot go into details because of the IP confidentiality. I'm working with the companies. What they're doing, up to now, they have 120 different design. And they set up a matrix. If it passes this, then it's a good cell. Okay. So at first is the design. So they play with, I show you 4 design, taking from them, okay? But there are a lot of design options, but they have a criteria matrix. If it passes all the 5 criteria, they said it's a best design. And then scaling effect, yes, we are not in that direction yet. Right now, we are doing 2 things. One is the design. Second thing is I'm trying to analyze the fatigue life. That is the next. And the third is we are also playing with the manufacturability to enhance the fatigue life. So these 3 things we are doing right now. But in future, yes, that is one of the area we might look. But up to now, new design and synthesis and fatigue life.
Thank you.
Okay, so thank you very much again, Mokarram, and I will ask thanks for the 3 speakers. So thank you all. Not sure, Iago, if you want to say something about the break now. And
no, I only...
You do better than me, so please.
You honor me, but you're a better scientist than a liar. No, simply we have a break now, okay? A coffee break. I invite you all to go outside and have, as I said before, a moment for networking, a moment for coffee, a moment for refreshment. And the people who isn't home, just remember that we're going to show the timetable here and we will come back after 30 minutes, I think, okay? Thank you very much. Welcome again to the Twilight Conference. Thank you very much for being here. There's a lot of people still in the room. There's a lot of people after the coffee, and I hope you feel energized and you're happy to be here and you're happy to learn with these three Masters of Science. I have the pleasure to introduce Abdon Pena-Francesch. He is a teacher in the University of Michigan, and he is the lead of the Multi-Biostructures Lab. And he's also, as I said before, that Daniel was the soul, the scientific soul of this Congress. He's the other part of that soul. Thank you very much, Abdon, for your help. Let me say only one thing. We're going to have a smaller roundtable right now because Killian Stenning is going to present from video conference. So I will introduce him later on at 5:20. Thank you very much.
Thank you very much, Iago. Thank you and welcome after the coffee break. It's my pleasure to moderate and chair this session. I wanted to first thank Patricia Sierra and Ivan, Guillem, Iago, and all the Monodon and also the INTA-SEIPAR team for hosting us today. This is very, very exciting. And well, we've had a session this morning on swarm robotics. We just had before a session on material and sensing. Now we have a very exciting session on neuromorphic solutions to underwater robotics problem. So our first speaker today is Professor Rafael Garcia. He's from full professor at the University in Girona, and he's the director of the Computer Vision and Robotics Institute, VICOROB. He's done very, very interesting work on underwater robotics, vision and 3D reconstruction for mapping, and of course, all the algorithms and all the reconstruction that happens behind the scenes. We're very excited to hear about your talk on next generation sensing for underwater robotics, Bioinspired and Neuromorphic Solutions. So please, let's welcome him to the stage.
Well, thank you very much. Thank you very much, Abdon. Thank you very much for the invitation and for giving us the chance to share here with you. We're going to talk about neuromorphic computing, whatever that means, okay? So how many of you here know about neuromorphic computing? Could you raise your hand? Okay, just a few. Okay, all right. I'll ask the same question in half an hour, okay? All right, this is joint work with Jat and Haya, two PhD students in our lab, and they are co-supervised with Professor Gracias in Girona. So basically, we are located in the northeast of Spain, and it's well known that Girona is like the reference place when you want to locate Barcelona. So it's 100 kilometers to the north. We have two buildings, and I'm going to show you this second building here, the SEARS. This is the Underwater Robotics Center at the Technological Park of the university. And this is what it looks like. We have a facility in which we can tinker with the robots. We develop our own robots. We basically run experiments. We have a boat also, because when things work in the pool, then we go to the sea and try to see if things are working. We have a very nice submerged room in which we can see what the robots are doing when we are running experiments. And what do we do normally? Basically, what we do is we work in autonomous robots. So we want the robot, like the Sparrows robot in this case, to go and download a mission, lift the surface, go down, start the mission. In this case, it's a mapping mission in which we want the robot to explore a given area. If the robot is finding some problem on the way, we want the robot to be intelligent enough to react. We heard this morning that communications underwater is difficult. So the robot has to have autonomy to be able to carry out tasks on its own. And then when it gets to the surface, either it delivers the data that it has collected, or in this case, if it has built a map, it can share the map or share the findings. Maybe in the map, it's looking for specific issues, and we want to use machine learning to detect whatever we want to detect in this map, and to, even if there are obstacles or problems, to react and replan based on those obstacles. We can do this type of maps in 2D and on the fly, or we could just collect the data, like in this case. This is an ancient shipwreck from the 2nd century before Christ. It's here in Girona, okay? And you know, the type of maps that we are getting could be more complex, like this one. In this case, this is built afterwards. So the robot is only aware of what is the trajectory that it's following, but in this case, it's not building the map in real time. So in some of the missions, at least what we want is that the robot must be able of what is the surrounding that has around it while while executing the mission, and then we want the robot just to be able to react in a proper way. And this is an example, for instance, from an European project called Eurofleets Plus that finished earlier this year. And this is joint work with Robotics, which is one of our spin-off companies. And in this case, we have two robots. We have a surface vehicle, and we have an underwater autonomous vehicle. And they are communicating, and basically the one on the top is just building, in this case, a bathymetric map. And in this bathymetric map is finding some objects, you know, these detections that are doing here. And then it's processing these in real time and deciding, is this an interest object according to the mission that we have that should be explored in a more detail by the AUV that it's underwater. And then when it finds something that is interesting enough, what it does is passes the coordinates of the object that needs to be explored to the AUV, and then the AUV is just replanning on the fly its trajectory so that it can explore the object. In this case, you see, it's just a concrete block, as an example that we did in the harbor in San Feliu de Guixos, which is where we have our boat. But you see, the robot has to be able, in mission time, to just sense the environment, measure things, transmit some information, just not images. We're just transmitting messages, you know, saying even when the robot is underwater, we just can ping the robot and say, are you okay? Yes, I'm okay. Did you find the object? Yes, I found the object. Are you exploring? Yes. This type of very short messages, and you see once one of the objects is explored, then it goes to the next object, and so on, and the mission is going on. So this is what we do. And up to now, we were doing this with traditional hardware, okay? So this means that part of the onboard processing is happening in GPUs. So this is computational, very efficient, but the problem is that, you know, their consumption, the battery consumption is large. And we have the problem that we have an autonomous robot, and an autonomous robot has to carry its own batteries. And if the robot carries its own batteries, we would like it to be on a limited budget in terms of the battery use that it's using. So what we are trying now is, okay, can we move from GPU to neuromorphic chips that are going to be more efficient in terms of computational, or the ratio between computational capacity and the consumption of battery. And this is what we are starting to look at some of the things that we're doing. And you have seen some of the things we're doing is using standard sensors, standard cameras, for instance. Everybody knows what is a camera. And here you see this array here. The data that we are collecting with the standard camera is just one image, and then a fixed time frame later, another image and another image. Say that we acquire 10 images per second. This means every 100 milliseconds, I'm taking one shot, another shot, and I'm transmitting this to the hardware. And what I transmit is a matrix full of numbers with RGB values that doesn't have any structure. And then, you know, the GPU card needs to process these, carry out convolutions, start looking at trying to extract features and trying to make sense of those features, and then try to decide, is this detecting the object I'm looking for or not? And 100 milliseconds later, again, even if nothing changed in the image, I give another image, and this other image, just the hardware takes it again, takes this matrix of numbers, extract features again. You know, it's very tedious to do this when nothing changed in the image. So the question here is, could we do something that it's not that computationally expensive? And the other thing that happens with the standard cameras is that sometimes if I don't have enough light, and this is something that happens underwater, believe me, then you get blurry images. And then, you know, these are bad, this is bad data to try to extract features and to measure if I have a fish here or if I have whatever object I'm looking for. So, standard cameras have very good properties. They are compatible with conventional hardware. and compatible with conventional vision algorithms, and it's a well-known technology. But the problem is that I might suffer from motion blur, I have data redundancy, nothing changed in the image, and 100 milliseconds later, I need to process again all those matrices of numbers just to find out that nothing changed in the image. And they have limited dynamic range, and they have high latency. From the moment something happens, because I have all this feature extraction and all this processing that I need to do, even transmitting the image itself every 100 milliseconds, this takes time, and I have a high latency. So, what can we do in a better way? We can look at biology, and we can use cameras that are inspired by biology. Remember here, we are on underwater bio-inspired systems. And what these cameras are doing, basically, is that instead of taking the brightness of every pixel, what the camera is doing is processing every pixel in an independent way, and then looking at what is the behavior in a temporal way of this pixel. If a pixel had a value, a luminance of 100, and in the next sampling time, this 100 has changed to 140, an event-based camera is going to say, yep, this pixel has changed. And this is an asynchronous event. And it's generating an event and saying, look, this pixel, I have changed, and I have increased my polarity. I don't know how much. It's just telling me, you know, an event has happened. And this is inspired on how our retinas are sending the signals of the images that we see through the nerve, through the optical nerve. These are spikes of things that change in the images because they are saying, you know, something has changed in texture. There's a change of texture. There's a change of color. There's a change in the motion that I have of the images that the retina is capturing. And in this case, one of the advantages is that I can save a lot of data that I'm transmitting to the hardware that is going to process these images. Look at this disk here. This is an example with a camera. This is a standard camera taking this 3D volume of images, one image, 100 milliseconds, another image, 100 milliseconds, another image, and transmitting all the images. But look at the event-based camera that we have in the bottom. So the event-based camera output is only showing what pixels have changed. And I only have one polarity saying, okay, this pixel has increased. That's an event. This pixel has decreased. That's another event. And you see, if there's no motion, no events are sent. So I don't need to waste time in processing these images. I don't need to waste energy in processing these images. And in this case, you know, the problem is that the traditional vision algorithms are not suited for this type of cameras, and we need to develop something that is different. And we have asynchronous pixels. Every time something changes at microsecond level, the camera is generating an event, is a spike that is sent to the hardware so that the hardware deals with it. And if I look at how this affects the response of the processing module that is taking care of these images, you see that on top we have the basic standard camera, one frame, and after 100 milliseconds, another frame. Well, here, you see, I generate events at microsecond level, microsecond resolution. So for every event, I just say, what is the time at which the event happened? What are the XY coordinates of this event? And what is the polarity? Is it an increase or a decrease of the luminance that was detecting this camera? And as a result, what I get is something like this. You know, instead of having a blurry image like this one, what I get is an image in which only the pixels that have changed are generating spikes. And the red ones will be polarity in one direction, the blue ones are polarity in the other direction, increase or decrease of the signal. And then what I get is a camera that has a much higher dynamic range, that it's not affected by motion blur, that the refresh rate and the latency is much better than a frame-based camera, than a standard camera, and the advantage, look at the power consumption. You know, because of the different technologies, I go from 1 watt to 1 milliwatt of consumption approximately for this type of cameras. Okay? Now, I have a camera that is generating these events. How do I process it? And the way to process them or one way to process them would be to use what are called spiky neural networks. Because event-based camera and spiky neural networks share that they are dealing with these spikes, these events that arrive at asynchronous times. And instead of using a standard neural network, artificial neural network. What is an artificial neural network? Up to now, all the neural networks that we were using in the videos that I showed at the beginning were standard, like CNN-based neural networks. And basically, they have some inputs. They apply some weights. These are the learnable parameters. This is what we learn. And then I weight every input by the weight, and then we sum all the outputs and apply a nonlinear activation, and I get a number that is between 0 and 1, and that's what I transmit to the next neuron, okay? In this case, I'd like to explain what is a spiky neural network. Imagine that I have a bucket, and on top of this bucket, I have several taps, and these taps are dripping water. And every drop that arrives is a drop that is increasing the amount of water in the bucket. And the bucket is basically going to keep this membrane potential, okay? So the memory or the value that I have in this spiky neural network is this membrane potential, which is like the amount of water that I have in the bucket. And then for the different inputs that I get, which is what is represented here, I get one event, and you see I had an initial empty bucket, and then it fills a little bit. For every drop that falls inside the bucket, I get an increase of this membrane potential. And the bucket has a small, tiny hole. So it means that it's leaking water over time. If I don't touch the bucket is going to be losing this membrane potential, is going to decay over time. And this is what you see here, that you have this value here, that one event arrived, this event here, and then the membrane potential is going down until another event arrives, and then I increase again the membrane potential, and then it decays, and then another event happens. And the information is encoded on the temporal distribution of these events that are arriving. And when the bucket is full, when the membrane potential arrives to a value that is larger than a given threshold theta, what happens is that the event-based, the spiky neural network is generating a spike. These are binary signals, okay? It's just a spike. And it generates this event that goes to the next neurons through the neural network and is going to be transmitted. It's quite surprising, isn't it, that we're going to encode information in this way, but this is how biology is doing it. And in some cases, depending on how we model the neurons, we could have also, after firing a spike, we can have some time in which the neuron is not firing another spike independently of the events that arrive, and so on. So this model is called the LIF neuron, the leaky integrate and fire neuron. It's one model of spiking neural networks, of one model of spiking network with which we can build more complex systems. But there are others that model even in a more accurate way how biology is dealing with this. All these neurons, the LIF neurons, we can implement them in neuromorphic chips. And basically, a neuromorphic chip is packed with this type of LIF neurons and these artificial synapses that then are only consuming electricity when these spikes are generated, okay? When these spikes pass through them is the only time. This means that most of the time, when I have a big neural network, most of the neural network might not be consuming energy because it's not receiving spikes that are activating these neurons, depending on my topology. And the nature of the spiky neural network is asynchronous in the same way that the event-based camera is asynchronous. So this is a very good fit that is going to work very well in my approximation. And as a summary, then what happens is that the energy consumption of the neuromorphic chip is going to be much lower than the energy consumption that I have with the GPU. And if we combine now the fact that I'm using an event-based camera, which is this thing here, I'm using this camera that is only is reducing the firing rate, the amount of data that it's giving to my processing system is only 5% compared to a standard camera that it's taking one frame every 100 milliseconds. And the neuromorphic chip, on the other hand, because I'm just accumulating these spikes, it's using additions and subtractions. And then this means that it doesn't need memory matrix multiplication, which is what artificial neural networks, standard artificial neural networks are doing. And this means that I'm being 80% more energy efficient, more energy efficient using neuromorphic chips. And then this turns out to be about 10 times less power requirement for my underwater robot. And this is very good because I have an underwater robot that needs to carry its own batteries. So in summary, using neuromorphic hardware, I decrease the firing rate, I decrease the number of active neurons at a given time, and the operations are addition and subtraction instead of matrix multiplication, and it's an asynchronous chip instead of a synchronous chip, and the power consumption is much lower. So this is a good fit, okay? Now, how have we used this type of approach? Well, we started saying, okay, let's try to see how the robot is moving. Let's try to measure how the camera is telling me something about the motion of the robot. And then what we want to do is to predict something that is called optical flow. I'm going to explain in a minute. And from this optical flow, I'm going to try to estimate what is the motion of the robot and find out what is the trajectory that the robot has followed. And to explain what is the optical flow, basically is a pixel-wise displacement of velocity or velocity vector in which I'm looking at in a given image. Here on the left you have a standard camera in which we are computing optical flow, and here is an event-based camera. First thing is you see that only the pixels in which I have events are places where I want to compute the optical flow, and in this case I'm encoding the direction of the optical flow for every pixel with this color wheel. You see, if it's pink, it means the motion is in this direction. If it's green, the motion is in this other direction. If it's cyan, is in this direction. And the brightness, in this case of this image, is showing me what is the norm of this motion. How big is the arrow of the optical flow. Now, we have designed some architectures. So basically, we designed two non-spiking architectures to compare with. With these two non-spiking architectures, we want to compute the optical flow, and then we will implement, I will show you the results, for 3 spiking neural networks in which we are using these LIF neurons, these spiking neurons, to see if we can match the performance of the state-of-the-art, okay? In both cases, we have the same UNet structure. This is a standard structure in convolutional neural networks. There's an encoder part here, then there's a residual, and there's a decoder part. What we're going to do is just to experiment with changes in the encoder, combining CNN or convolutional blocks with spiking blocks for processing these images of the event-based camera. The first model that we implemented is like the standard architecture for solving the problem of optical flow, which is a convolutional gated recurrent unit, this COMGRU that you see here. Basically, it's using recurrency in the encoder block to capture the information on the sequence, because I'm going to give a sequence of temporal information, and then it's encoding this information. The second architecture, the second non-spiking architecture that we implemented is an architecture in which instead of recurrence, we are just not using recurrence, but we are taking we are carrying out 3D convolutions. This is why we call the model COM3D. We are applying, taking a slice with a few of the frames of events that we want to process, and we carry out convolutions in depth so that we take into account the temporal change. And then we have 3 spiking architectures to compare with these first 2 that I showed. The only thing we're doing here is basically after every downscaling block with all that we have here within the encoder, we place this red thing here and this red thing here, and these are basically the spiking activations. Okay, and this is where we are going to place our learnable spiking neural networks, spiking basically neurons. And we have tried 3 architectures. The first one, I call it ConfSpike. In this case, we're using standard LIF neurons. In this case, there's no recurrency, so we are relying on the membrane potential as a memory unit to be able to take into account what is happening over time, the motion that is going to happen. Then the next one is the ConfRSpike. In this case, instead of using LIF neurons, we are using recurrent LIF neurons. So in this case, the output of the neuron is just being fed back to keep this recurrence and to be able to process the sequence of events. And finally, we have like a combination of convolutional gated recurrent unit in which I have recurrence and then LIF neurons. So let's have a look at the results. This is basically the background or the reference. We have here what are the events that were generated. This is the ground truth. In this case, we're using this data set here, the MVSEC data set. This is a data set acquired with a drone by the University of Pennsylvania. This is the reference of the data set. And the reason we were using this data set is because, they put several data sets in which they have ground truth in the representation, in the measurement of the optical flow, because they were using, Velodyne, and it was an environment in which they could measure what is the real motion that we should have for every pixel. And then here we see what are the results that we are getting. And you see, well, it's very dark, but you see that the two results on the top row are the non-spiking networks, and here I'm showing the result of the last two spiking networks. The reason I'm showing only these two is because the first one, the one that was relying only on the membrane potential of the LIF neurons, did not converge, did not generate good results. So we saw that we need recurrence for the network to learn. But the other two are getting, you see, if you look at the flow and you look at the ground truth, we see that, the results that we're getting from a qualitative point of view are quite good with the spiking. And this was, a very positive result on our side. And then we decided, okay, let's have a look. I should say that we use one sequence for training of this University of Pennsylvania, and then we used two other sequences for testing. And these are the results for the two sequences. The indoor flying 2 is a test sequence that we didn't use for training, so it's just to see how well the models are working with a different data set, and the outdoor day 1 is another different test sequence. And what we see here is that, all models perform very well. The best performance is obtained with the ConfGRU, which is the state of the art, okay, is the non-spiking architecture. But, the two spiking architectures that we tried are getting pretty nice results. This is average endpoint error. So basically measuring the average Euclidean distance between what the motion of this pixel should have been according to the ground truth and what it was. And the endpoint, I'm just measuring, I'm taking the Euclidean distance and doing an average for that. You see, we have an average error of around half a pixel. So the results are very decent. But there's something curious here, which is this indoor flying 2 sequence was quite similar to the sequence that we use for training. And then we applied this outdoor day 1 sequence, and this sequence is somehow different. Here we wanted to see how well are my spiking neural networks generalizing to a different data set that is much different from what I used for training. And then what we see here is that, they still work, but the degradation in the performance is slightly higher than what we have with a more simple, a more similar testing data set. And in this case, what this means is that probably, we see that spiking neural networks work, that we can use them, but the generalization capability of these networks is probably less, and they need more data. They need more richness of data to be able to learn, probably because we are using spikes. And, when I try to backpropagate the gradients for a spike, we need to use surrogate gradients and approximate the spike by some continuous sort of step function, and be able to propagate these gradients. And this is probably not getting that well propagated. But the important conclusion here is that we get, comparable performance, at least. Not improved, but, at least good enough performance. What did we do then? Then we took our event-based camera. We have two event-based cameras, the Davis and the Prophecy, and we put them in the underwater housing, and then we used the same robot that you saw in the morning, the toy robot, the blue robot, and we started collecting data with this setup. This is on the right, the type of events. In this case, the Davis is a hybrid camera. It has a black and white sensor and an event-based sensor in the same housing, and then you can compare. But what we saw is that, if we want to train these networks, we don't have any underwater sequences. In fact, this is the first event-based sequence that we see underwater so far, according to the literature. And because we need to label all these pixels, or these events that are happening, probably it's going to be very difficult to get the amount of data that we need to generalize in a proper way and to make these systems work in real scenario with our underwater robots. So what we saw also that there are no publicly available data sets captured underwater, that most event-based simulators do not support complex dynamic environments, and there's no standardized format for event-based camera, because this is quite new. And then what we did was, okay, let's create our own library, EWIS, that is going to help us for processing and manipulating event-based data sets. And we have the Stonefish simulator, which is a simulator that we developed at the University of Girona, and we just added the we modeled event-based camera on the simulator so that we could generate synthetic data sets. And one of the nice things that we saw, this is an example of the blue rove in our simulator, this is the Stonefish. We created a scenario, which is this one, and then we see here, this is the grayscale, or the color in this case image, and this is the event-based camera. So the nice thing about this is that I can generate many sequences in which I get the ground truth. And then I can use these sequences for training my event-based camera spiky neural network. And I'm going to be able to then try many different types of motion, scenes, and so on. And the other nice thing is that the gap that we have between simulated data and real data when I use RGB images is large. But when I use simulated spikes, simulated events, and real events, the type of data that I'm getting is very similar to what I get from the simulator. So the gap that I have between reality and simulation, in the case of an event-based camera, because these are only these binary spikes that have only polarity positive or negative, it's going to help in generating data sets that are quite, I would say, similar to what I'm expecting for training an SNN, a spiky neural network. So, as conclusions, we have seen that event-based cameras are a good approach to overcome motion blur, have low latency, and overcome the dynamic range limitations that we have underwater, where we have light absorption, and we have this challenging environment for using standard cameras. We have seen that spiky neural networks have comparable performance with respect to traditional or state-of-the-art solutions based on convolutional neural networks, at least for computing optical flow and using this for ego motion of an AUV. So this is a feasible thing to do. And both spiky neural networks and event-based cameras offer a low power consumption solution, which is very good for an autonomous robot that needs to explore the environment. And then this means that neuromorphic systems are a good fit for autonomous underwater vehicles. Then what is next? What I can do now is, okay, if I look at my robots and the sensor suites that they have, I see that, for instance, I have a sensor that is called DVL, a Doppler velocity log, which is giving me the speed of the robot with respect to the seabed when I'm navigating close to the seabed. But the problem is that if you have irregular seabed, or if you go to a place where you have some 3D structure, because I'm inspecting just some oil structure, some oil infrastructure, for instance, the DVL becomes very inaccurate, because it only works when you have, when the beams that are using the Doppler effect are bouncing back from a more or less flat seabed. And then the refresh rate that I have is also very low compared to cameras. So what we can do is, in these situations, I want to use an event-based camera, because when we are close to structures and we have 3D relief, event-based camera is going to work very well. And the other advantage is that it has a very high refresh rate. So I can integrate these in my AUV, in this case in the Girona 1000, so that we can use or develop this underwater visual odometry system that will allow the robot to just have a good estimate of how things are changing in the environment and how the robot is moving. Okay? And I'm going to skip this one. And how are we doing this? Because now, what we want to do is just, we have the event-based camera, we have the underwater housing for the camera, but we still don't have the neuromorphic chip to make this, to run in the robot itself. And in this case, we have a project with Intel. Intel has developed the Loihi 2 neuromorphic chip and has developed a software framework. This software framework is called Lava, is similar to PyTorch. And we have access already to this infrastructure, to this software framework in which we can already design our own architectures and run the hardware, or run the designs or the architecture of the spiky neural networks on these neuromorphic chips, and we're going to get in a couple of months the first board that it's carrying 8 Loihi 2 chips, and this is programmed also with the same Lava framework, and then this means that we will be able to run the spiky neural networks directly on the hardware that it's embedded and it's being carried by the robot. And we also have a cooperation with a German company called SpinCloud. SpinCloud is a spin-off of the university of a German university that is cooperating, in fact, with the University of Manchester, and with the team of Professor Christian Meyer. And this group, in fact, was the one that developed the Spinnaker board, that it's the main board that was used in the human brain project. And now they are developing in fact, they are building a custom board for us that it's going to be ready quite soon, together with the software framework. Is the Spinnaker 2 that has 4 of these chips, and again is a neuromorphic hardware that could be integrated in the robot and could be in an easy way. We can implement with the software framework the SNN that then will run directly in the neuromorphic hardware. And on the other hand, we have we also have access through eBrains. eBrains is a microservice, and we have access to the infrastructure. Is a microservice from the Human Brain project, and here we have like a research infrastructure in which we can model more complex type of neurons, even more complex than the LIF neuron that I showed you before, and we can just design architectures and then try this directly on their own hardware. And finally, we're cooperating with ELTE, which is a research group in Budapest. In fact, we have an Erasmus Mundus Masters with them, and with them we are now working on the development of new architectures for spiky neural networks and some other projects. You know, we are trying, for instance, to see how to train a neural network, a spiky neural network, using gradient-free and a gradient-free approach in which we don't need to pass these gradients through this approximation of the tanh and so on. So basically, this is, I would say, the steps we are taking in this bio-inspired approach, trying to, you see, we're not trying to have more computational power. We are trying to save power, in fact, so that the robot can carry a smaller battery or can last or have longer missions with the same budget of battery. And then finally, I would like to thank, special thanks to the Jad and Hayat, which are the 2 PhD students working on this, and Nuno Gracias, and to the rest of the team that is waiting for you in Girona. By the way, we just finished last week the renovation of the Underwater Robotics Center, so you are all invited to visit us and see the new facilities. So thank you very much.
Thank you. Thank you very much, Rafael. I have to say, I do have some colleagues that work on neuromorphic computing, and I say I understand, just to be polite, but I don't really. But I think this is the nicest introduction to neuromorphic computing, and definitely I think Vision makes a very compelling case to illustrate all of these things. So beyond all the excellent technical work, this has been very educational, I think. So I really, really appreciate it.
Thank you. I forgot to ask, how many of you? I'm not going to do it.
We'll take questions from the audience. Yeah, please.
Okay, so sorry to ask too much, but okay, Rafa, was a nice presentation. My question is more referring to the other like opponents of GPUs, neuromorphical or neural processor units, talking also about FPGAs. I have listened about neuromorphical processor unities since 10 years ago, so right now it's like in top trend because Apple and all these companies have been doing a lot of ads for that. But normally when you see a robot underwater or a drone, they use Jepson Nanos or this kind of GPUs to process for sure. But when you have a lot of information, not only coming from LiDAR, for sure you are working underwater, you also need to handle this amount of information, not only for this sensor, but for all the sensors of the unities. Why not use FPGA that maybe you can reconfigure at some point? If these MPUs you can only configure once, and then you need another chip to do that. That's really my question.
So, in fact, we are using Jetson Orin and Jetson Nano and this type of solution. So up to now, like the first videos that I was showing with the results, we have been using GPUs. Basically, some time ago we were using FPGAs also for accelerating some of the tasks, and even allowing us to just change the configuration of the FPGA so that they could adapt for very specific tasks in which we need to process and do some types of very fast operations. And what I would say is that probably in the coming years, edge computing has started to play a role. And until now, most of the papers were about, yeah, we are doing these fancy things. Look at what is happening now with ChatGPT and all large language models. Everybody's saying, oh yeah, mine is bigger and inference time is shorter, and so on. But at some point, this is also going to go back to edge computing, and what can you do unplugged from the internet, and trying to find a solution for your problem. In our case, it's very clear. It's an underwater robot. Communications are not feasible. You don't have a tether that it's connecting to the surface, and then you need the robot to be able to compute on its own. So I don't know how to answer your question, to be honest, but I think in the near future, we are going to see many more solutions that are going to look at the efficiency of the processing that we are doing on the edge. And this is probably where we're going to see not only neuromorphic chips, but we're going to see also probably FPGAs are going to go back for specific tasks. One of the advantages of the neuromorphic chip, on the other hand, is that out of all the circuit that you have, the neuromorphic chip, in some of these frameworks, they allow you to reconfigure on the fly, for instance. And depending on when and what you need to do, you can change part of these cores that it's going to have, and the interconnections that you have. So somehow these neuromorphic chips also are saving energy, because in most of the time, the hardware that you have there is not working because spikes are not generated, and then you are saving time during those periods of time. And that is a great save in energy compared to GPUs that are just doing matrix multiplications all the time. And then this is why you need a lot more energy. But yeah, it's interesting to see how this edge computing is going to move in the coming years.
Great, thank you. Do we have more questions? I think
there's a question from home here, so I will not provide context because I only know the question. And it is exactly, have you tried self-supervised methods to eliminate the need of labeled data?
Not yet, but we are working on self-supervised for other problems. So, for instance, we have trained a transformer in which we were training. This was a transformer for doing classification of seafloor, and in this case we had a small amount of data that it's labeled, but a large amount of side scan sonar data that it's been acquired over the years. And then that's the place where you want to use self-supervised methods, in which you leverage a small amount of labels with a very large data set that it's unlabeled. But certainly, this is one of the ways we're going to go in the future, for sure.
Great, thanks. Do we have any more questions? If not, I have a few, but maybe I'll ask one while we maybe change the speakers. It's very exciting that you're setting up a data set, for underwater models. From a practical perspective, right? Because this, it's a much more dynamic and irregular environment, right? So what are the challenges that you're seeing for establishing this, not only for your lab, which obviously works great, but to providing this to the community?
So getting data is expensive, normally. Finding a problem in which the gap that you have between simulated data and real data is so small is very appealing. And because we had the stonefish simulator, it has been relatively easy for us to just integrate these sensors in the simulator and then be able to generate sequences. And now we are preparing with my team. We are working on generating large data sets that then could be used and could trigger more groups to just use event-based solutions, and then to also develop spiking neural networks, like, in fact, the steps that we are taking. So this could be, like, the first steps in the future. And I think an event-based camera is a very suitable, very adequate sensor for underwater because of these characteristics that it has that I explained about, there's no motion blur. If you have very rapid motions, nothing is, you're going to get your signal still.
Yeah, very, very exciting. Yeah. Thank you very much. Please, let's thank Professor Rafael Garcia again. Great. I think next we have Professor Arnold Mitchell. I think things working okay? Yep. Okay, perfect. So Professor Arnold Mitchell, he's from RMIT at Melbourne, Australia. So I think probably he's the one of us that has traveled the farthest to come here. So we really appreciate you joining us for the conference. He's a distinguished professor at RMIT, and he's also the university director of their Micro Nano Research Facility, and also the director of a brand new center they have, ARC Center of Excellence for Optical Microcomms for Breakthrough Science, the COMS Center. He's been working on in addition to data communication, to designing on photonic devices, then it's a very big breadth of work. But I think today he's going to talk on their microchip development and using light, sound, fluids, and electronics for data communication. So please, let's join me in welcoming him. Thank you.
Thank you very much. So, thank you very much for inviting me to this. I've got to say this is a little bit outside my field. I'm mostly a photonic chip person, and we're exploring the opportunities for underwater, but I have a lot to learn, so I look forward to talking to you all about that opportunity. I'll probably spend maybe 60 to 70% of this talk introducing some of the work that we do and the COMS Center itself. It will eventually arrive at Neuromorphics, and I think will complement some of the things that we've heard about already. So let's see how we go as we go. So the first thing I should mention is I'm from RMIT. RMIT is actually a pretty big university in Australia. It's got about 90,000 students, and unusually, and I've tried to expand Google Maps to its largest so that we could actually see where we are in reference to where my home institution is in Melbourne, but it's actually right in the middle of Melbourne City Central Business District. And so you can see, this is a shot of Melbourne, and you can sort of see, let me just put my laser pointer on. Here we go. You can see the RMIT logo there. This is Melbourne Central Railway Station, and that's my office there. So it's quite close to the centre of the city. We have, you might wonder, okay, why have I travelled almost entirely around the globe to come here? And how did I get involved? So RMIT has a research office in Barcelona called RMIT Europe. It's been running for at least 10 years, and it specialises in coordinating sort of European Union actions, particularly doctoral networks. And so one of the things, actually, another thing I've been doing while I'm here is a doctoral training network, particularly between France and Australia, but not to be left out, we have also put in a postdoctoral training network between Spain and Australia. So that's just sort of coming together now. It's just been awarded, and we're looking forward to particularly working with Navantia on that project. So my own research team at RMIT is the Integrated Photonics and Applications Centre, and basically it sort of has an engine room, which is sort of the design, fabrication and packaging of photonic chips. And I get very excited about these photonic chips, but to most other people, they're fairly dull because they're sort of these little grey squares with features you can't see on them, and they often work on light that you also can't see. So that's very hard to get people excited about. So we emphasise the applications, and I'll go through some of the applications in a little more detail. So running that engine room, I have a design expert called Tak Nguyen who does all of our simulation and theory and design, and then the fabrication team is run by Guang Hui Ren. Probably our team at RMIT is about 50 people, so it's a pretty big group of people, and maybe a third of them are sort of in this engine room. And essentially what they do is they create designs of integrated circuits using laser light, and then we make prototypes. And we have all the facilities actually in the city at RMIT to fabricate these chips as well as design them, and package them, and then put them into a format where we can potentially use them. We work on silicon, which is sort of the industry standard, and silicon nitride is emerging as industry standard. But one of the areas we really specialise in is lithium niobate. And lithium niobate's quite interesting. I've been working on lithium niobate since I was a PhD student, and it's interesting because it actually has acoustic properties. It can be used for surface acoustic waves and piezoelectrics. It has RF properties. It's sort of the interface between analog RF and laser light. And it's also really good at photonics, and it can convert light from telecommunications wavelengths to visible, and it works all the way from ultraviolet into the mid-infrared. So this is pretty exciting. It covers, I think, all of the areas that we heard about this morning for underwater communications. So, it seems like a pretty good platform. We're interested in trying to make quite complex integrated chips that deal with laser light, acoustics, and RF all in the one package. And the idea is that if you can integrate them together and package them, that can be more robust, which I think would be quite important if you're sort of operating, sort of deep in the ocean, actually having not a lot of moving parts. Everything's integrated into a monolithic chip. Okay, so that's enough about the chips themselves. Let's talk about some of the applications. So very briefly, I knew that there were going to be some people talking about soft robotics today. So I wanted to say just a few words about our biomedical team. That's led by Cesar Huertas, who's actually did his PhD in Barcelona. And he runs this team. And this is a sort of an example of a chip that we have. So this is the photonic chip you can see here. Each of those little squares actually is a sensor, and you've got, it's a Mach-Zehnder configuration, so you've got a reference arm here, and then a sensing arm, which is a big coil. And you functionalize that sensing arm with antibodies to whatever you're trying to sense. And as the thing that you're trying to detect attached to the surface, you can actually measure the phase change that you get with that. One of the applications we've done in collaboration with ICN2 here in Barcelona is looking at antibiotics in seawater. So when people farm, the antibiotics they use run into the rivers, and that runs into the sea, and you can measure trace amounts of antibiotics actually in the ocean. So that's one of the things that we were working on. This is another example. So we marry those photonic chips with microfluidics. And so this is an example of one of our active microfluidic devices. You can see there's pumps and valves and active fluidics going on there. This is all made with a one-shot injection mold. So it's sort of a technique that we developed, and we're able to sort of design something like that and actually be fabricating prototypes in a couple of hours. So it's really, really good for rapid prototyping. And this particular chip was used for looking at blood clotting, for example, but you could imagine how you might adapt it for sort of soft robotics. Okay, enough on that. Another team works on sensing and metrology, and this is probably closer to the area that might be interesting for underwater. This is led by Andreas Boas, who used to be a postdoc with us at RMIT, but has since moved to Adelaide University. So this team looks at things like LiDAR, so using laser range finding and then forming that into images. We also look at things like gyroscopes, and so movement sensors. And if you put those, you can imagine if you've got a drone that's flying around trying to create a point cloud, as the drone's moving, that point cloud, all the points are going to be deregistered. So if you can actually keep track of how the drone is moving, you can re-register all those points and actually get a good image. The third ingredient, if you actually want a proper positioning and navigation system, is time. And so we're also working on trying to sort of integrate optical atomic clocks into these things. So if you don't have access to GPS, you can potentially have all of those things integrated together. And again, this is something that's very important if you're trying to sort of operate underwater. So these are 3 Australian companies that we're working with. Baraha for LiDAR, advanced navigation, do a lot of the work on inertial navigation systems using gyroscopes, and Quantex is a company started up in Adelaide looking at integrated optical atomic clocks. All right. The last application area that we look at is communications and a little bit of information processing, and this is really where the sort of neuromorphics come in. This is led by Bill Corcoran, who's based at Monash University. And one of the things we have done is really focus on these things called microcombs. And I'll explain what an optical frequency comb is in a moment. But suffice to say that this is a picture of a microcomb. So basically this big disc in the back is a Australian $2 coin. It's one of the smaller coins in our repertoire. Most of us don't usually use coins anymore after COVID, but there's one anyway. And this is the chip, and you can see just in the corner of this chip there's a little ring. That's what it is here. So it's less than 1 millimeter across. And what happens is if you put one laser wavelength into that ring, what comes out is maybe 100 laser wavelengths, all equally spaced in the communications band that you can amplify with an erbium depth fiber amplifier. And so this is sort of an image of that spectrum here. So you can see this green area is the area that you can amplify, and there's about 100 comb lines there. And so what we did was we basically took each of those comb lines and used it as a communications channel. And the quality of the comb lines, they're very, very low noise because of the way they're formed, and they're very, very uniformly spaced and very stable. So you can pack a lot of information in to each of those channels. And so that's what we did. This is a what's called a constellation diagram for communications, where each of those little dots is sort of like a symbol that you can use for communication. So instead of ones and zeros, you can have lots and lots of different symbols. One axis is intensity, the other axis is phase. And so you can pack a lot of information into each what would be a bit, and achieve a very, very high data rate. And so back in 2020, we actually achieved the world record communications link between our university here at RMIT. We've got a dark fibre that runs between RMIT and Monash under the city, out into the suburbs, and then comes back again. And so we demonstrated 50 terabits per second over that standard fibre that has been in the ground for 30 years. Nothing special about the fibre, it's just the the power of this very, very stable microcombs that we were able to achieve. And that got a lot of attention, and on the basis of that attention, we applied for this comb centre. And this is the biggest bucket of money that we can get in Australia. So the Australian Research Council funds these major initiatives for 7 years and offers $35 million, so about $5 million a year to really do something substantial. There's 8 universities that are involved in that, and each of the universities put in a similar amount of money. So we were, between us, have about $70 million Australian, which is significantly less in euros, to see what we can do with these microcombs. So just a little bit about what is a frequency comb and then what is a microcomb. So optical frequency combs, they're invented in 2000, and essentially what they are, they're like a clockwork. And so lasers are really good at measuring things, and particularly they're used for measuring distance and for measuring time. And by measuring time, they're essentially used with atomic species and trying to measure the energy difference between different electronic levels in atomic species. And these are those atoms are the same all around the world, so you can use that as a reference. A good example is cesium or rubidium. You can use as these references. But the issue is that you can't actually measure that oscillation frequency directly. You can see the color of the laser, but you can't actually measure what is the frequency directly. So the optical frequency comb basically gives you a whole array of these lines, and if you beat 2 of those lines together, you can actually measure that electronically. So they can be 10 gigahertz or 100 kilohertz or those sorts of frequencies, but that are accessible with electronics. And so what that means is that if you can tune your laser and then measure the beat to one of those lines, you can actually get a direct measure that you can measure off with electronics of what the frequency is. And that's sort of the power of these optical frequency combs. You can also turn spectra, for example, in the mid-infrared, into an electronic measurement as well. And so this is a way of actually doing spectroscopy, for example, for gases in the atmosphere. So this was regarded in 2005 as sufficient to be awarded the Nobel Prize in Physics. And so you can see John Hall here and Ted Hench standing next to optical frequency combs. This is Scott Diddams, who's part of our centre, looking at a frequency comb that he put together for astronomy. But you'll note that they're quite big. They're sort of about the size of a fridge. They cost about $1 million each, and in general, they need constant maintenance, about every 2 weeks by sort of PhD qualified people who really know what they're doing. So perhaps, because of that, you'll find them in a lot of very specialised laboratories, but they aren't really suitable for deployment. And you certainly couldn't imagine having one of these on one of the drones that we just saw before. And this is our science communicator standing next to one in Adelaide for scale. So about 10 years ago, it was shown that you could achieve these sorts of frequency combs using microchips. And what we've seen recently is that while it's been possible to make photonic chips for some decades now, the semiconductor industry is actually starting to really take these up and make them at scale, because of the adaptation of artificial intelligence, the amount of information that data centers are having to move around. The only way to do that is with photonics, and so they need to actually be putting photonics on the computer chips that are actually doing the processing to get the information off fast enough. And so we're looking to sort of jump on that opportunity and actually use the ability to mass manufacture these photonic chips as a way of being able to make these optical frequency combs generally accessible and hopefully manufacturable at scale. So our centre is half the science and technology of frequency combs and half the applications. And so some of the areas of applications are sensing and measurement, spectroscopy and microscopy. We've got a little bit of work on astronomy, but also information and intelligence. And so there's high-speed communications, but also trying to do some information processing, some filtering, some pattern recognition, before the light, a lot of these sensors are light-based. If there's all this information coming in the optical domain, can you process that before it actually hits the computer, or help the computer in some way? So a few examples. One of our researchers is a seismologist, and she's using these optical fibers to measure earthquakes, actually. So there's optical fibers that are already in the ground used for telecommunications. If you listen to the echoes of the laser light that's sent down those fibers, you can actually see if the fiber's being stretched or compressed, and you can actually see the earthquakes arriving. You can also see other things, like you can see lightning strikes, or you can see the rain falling, or water flowing in pipes. You can measure how full those pipes are and how fast the water's flowing. You can see cars driving over roads and trains and trams and even foot traffic. So you can imagine how you could use these sorts of measurements for early warning of an earthquake arriving. You can imagine how you could use these for management of drains during floods, for example. So the issue, though, is that the amount of data that's being generated by even one of these fibers is vast. It's terabytes every day, and Megan Miller's laboratory actually is a supercomputer, and it takes her several months to actually process all the information to see what the earthquakes are doing. And so what she would really like is to be able to do that in real time. And so what we're looking at is trying to use with these microcombs to actually process the information so that it's easier to detect. And I'll say a little bit about how we're doing that in a moment. I won't say too much about the astronomy, but essentially what Jean Brodie, who's an astronomer, is trying to do is look for Earth-like planets in sun-like stars in other star systems. So the way you do that is by looking at the colour of the star, and as the planet is going around the star actually wobbles back and forth very, very subtly, and it changes its colour because of the Doppler effect. And so you're trying to measure that change in colour, which is very, very small indeed. But the issue with that is that it takes years. So it takes a year for the planet to go around the sun, and so you're looking for this oscillating colour shift that might take 10 years to actually measure. And the issue with the frequency combs is every 2 weeks they're being maintained and recalibrated, and so you don't have a stable reference. And so what she would like is a sort of consumer electronic type frequency comb that would last for decades without any sort of maintenance. And so again, this is the sort of thing that you might like in an underwater system. The last example is Kishan Dalakia, who's working on spectroscopy, and he's sort of a microscope expert, and he's looking at sort of living organisms using sort of advanced microscopy techniques. And we can think you can use optical frequency combs for both spatial imaging, a little bit like LiDAR and sort of image formation, but also spectral analysis, so being able to sort of understand the sort of chemical properties of the specimens. But the issue for him and the issue for us in this room is that most of the frequency combs that we work on have been developed using telecommunications technologies, and so they work at infrared wavelengths around about 1.5 microns, which water is quite absorbing at, and so most living organisms are in water or made of water, and he really needs them at sort of visible wavelengths. So that's one of the things that we're really looking at, is trying to shift these frequency combs from the telecommunications band down into visible and even into ultraviolet, which is important for some of the spectroscopy, but also for this astronomy applications. So there's 18 investigators across Australia. Actually, the centre will probably grow to about 200 people. We've got about 100 members already, so we're still recruiting. So if you're sort of looking for a PhD opportunity or a postdoc opportunity, let us know. But essentially, we've got now 6 years, so we've been running for about a year to try and make these frequency combs smaller, more compact, and working at visible, but also to look at what we can do with them. And so this is really why I'm here, is to see, okay, is there an opportunity to use these frequency combs for example, sort of imaging underwater, or for underwater communications? So the challenge with underwater is, here's just the sort of water absorption spectrum. I'm sure most of you are pretty familiar with this, that basically shows that when you're getting up to sort of, the infrared frequencies, the water absorption is many, many orders of magnitude more than it is down in sort of the blue, and it's sort of best down just into the ultraviolet, but blue. Now, why do we choose to use infrared in optical fibres rather than, because there is a little bit of water in optical fibres? The answer is because the Rayleigh scattering is the best. The reason the sky's blue is because there's a lot of Rayleigh scattering, and blue is scattered more than red, so you see more blue. This is also true in optical fibres. So you're sort of balancing the absorption of the water in the fibre with the Rayleigh scattering, and that's sort of best around about 1.5 microns. This also plays out in water communication. So if you're deep in the water where there aren't many particles, then perhaps you're better off with blue. But if you're in shallow water and it's turbid and there's a lot of particles around, you've sort of got to know a little bit about your environment, and you might be better off with green or red. So the first idea is then, okay, if we were trying to get broadband communications, could we just use the same technique that we used in fibre in free space? We have shown that we can. So we've actually done a laboratory demonstration with 2 telescopes and shown that you can get, about 1 kilometre's transmission of the same data rate in free space. So that's so far so good. Could this be transferred to blue? And there's some examples in the literature where people have done something a little bit like that. So that seems to be a reasonable approach for deep water communication. Now, more subtly, what we might do with turbid water, the issue with turbid water is, you've got the scattering, which means you lose light, but it also means that it sort of bounces around and you get sort of echoes. And so if you've got the light increasing as a pulse of light, by the time it actually gets to the receiver, it's bounced around so much that it's smeared out that it might have actually crashed into the next pulse of light. And so your communications rate is really limited by this sort of diffusion of light through this sort of turbid media. And so this is where I think some information processing, and particularly some adaptive information processing, could be beneficial. And so I've got a rather technical diagram here, but I'll try and explain it as simply as possible. We have one of these rings that we put a single laser line into, and what comes out is 100 laser lines. There's a sort of magic box here that allows us to control the amplitude and phase of every one of those lines. So we can basically apply weights to each of those lines. And where we were using those lines independently as communications channels, so each line has different information on it, now what we're doing is we're putting the same information onto all 100 lines. Then we delay them. So what we do is we put a set amount of delay. We use just a piece of optical fibre to basically put a stepped amount of delay on each of those different wavelengths. And what that allows us to do is basically take the same information, and if we look at the line in the middle, once we've done the delay, the wavelength sitting next to it is a little bit in the future, and then the next wavelength is a little bit further in the future, and the wavelength on this side is a little bit in the past. And so you can then have all at one time essentially the time domain shape of that pulse, and then you can process that by detecting it and applying all the weights that using these different this thing called a wave shaper, and that allows you to do filtering and phase manipulation. So an example we did nearly 10 years ago now was what's called a Hilbert transform, which allows you to sort of study the phase of RF waveforms. This is useful for radar, for example. And this just shows us that we can achieve, if you put essentially a hyperbolic function on this, you end up with a flat intensity response, but a 90-degree phase shift on things. So this is quite a difficult thing to do in other ways, but we can program this filter to basically give us whatever response we want. We then went a step further, and this is a couple of years ago, and instead of using the different colours for the different delays, we actually put physical delays on a chip. and then basically dialed up the filter response that we wanted. But in this particular investigation, we actually sort of let a computer or used an algorithm to adapt the weights that we needed on each of these different delays to give us the optimal response. And so firstly, that allowed us to, rather than having to canonically say this is the response we want, and this is the Fourier transform of that response, the system could learn that. But it also adapted and overcame imperfections in the chip and the actual fiber system that it was built into. So you didn't have to. It actually gave you a better response than you would have if you just used the canonical thing. So there's sort of an element of machine learning. So the last thing that we did was actually use that technique and go one step further and actually have a second step. So we have had the weights that we could control to sort of put together a kernel. The delays allow us to sort of achieve a convolutional effect, and then another layer of light to act as a neural network. And so we were able to show that you could actually do pattern matching and classification with that system. And so I think the opportunity is to use something a little bit like that, use it with a green or a red microcomb, and then essentially try and unscramble the scattering that's happening with the turbid water to use all these different 100 laser lines to essentially reassemble the pulses that you achieved. And so this is something that we're looking at the moment. So, just harking back to the opportunities, lithium niobate, the platform that we work on, it will work at all of these different wavelengths and can actually wavelength convert. So one option is we can either have the lasers native at blue and green and red, and just as some examples of some of the chips that we've got in our lab operating at those wavelengths, but we can also use lithium niobate to take the telecommunications wavelengths and the combs that we already have and shift them down to those visible wavelengths. So this is my last slide. If you're interested in getting involved, feel free to make contact, and thank you for your attention.
Thank you very much. Thank you very much, Arnan. I do remember when the news came about, the connection between, you guys and Monash. I didn't make the connection that it was your team. That was very, very exciting and very promising. I think I did work with some photonics folks that, they show me some of the comm systems, and it reminds me a little bit of the early computing when they have like the big Turing machines. Now it's really impressive how you can miniaturize all these devices. So really, really exciting. We're going to take questions from the audience. Anybody? No? Okay, so give me some signs that we have to wrap things up soon, because we have the next speaker that is ready online. But before we move on, please let's thank Professor Rana Mitchell again. And I do have some questions, but I'll follow up with you later. It's very, very exciting. So I think Iago is gonna introduce.
Yes, thank you very much, Abdon, Professor Arna, Professor Rafa Garcia. Thank you very much. So we're at the last moment of this conference, first day. Tomorrow we have another day with a lot of topics, with 3 more roundtables. And we have a person, Killian, who is connecting from home. Please, Killian, unmute yourself. Let's check if you... Speak, please.
Hello. Hello.
Hello. Can you hear him? Yes. Okay, Killian. The stage is yours, okay? Thank you very much. If you want to stay here, you can, and if you want to go down, you can go down as well. Whatever you prefer, it's okay for us. Thank you very much. Killian?
Okay, hello everybody. I've got a bit of an echo coming through. So yeah, hello everyone. Apologies for not being in there in person. I'd just like to thank the organisers for the invite and for accommodating me online today. So my name's Killian Stenning. I'm a research fellow at Imperial College London, And I've spent maybe the last 3 or 4 years of my research career looking at neuromorphic computing systems, and in particular, nanomagnetic systems. And so today I'm going to give you a bit of an overview of the types of computing that we can do with those systems and try and link that into the general theme of this conference. So I'll start off just by giving you a bit of a background, and we've had an excellent background earlier that I'll add to, of why we're developing neuromorphic systems. So particularly looking at the AI energy problem and the kind of limitations of current hardware. I'm then going to introduce to you nanomagnets and why they're good for neuromorphic computing, and I'll show you some examples of the types of computing we can do with those systems, and then discuss some limitations and how we can overcome those limitations by making physical neural networks and interconnecting different systems together. So I think we're all aware of just how much AI is advancing at the moment. It's in the news all the time, but I think what's being increasingly spoken about and a concern is just how much energy AI is using. So just some small facts. 10 Google searches is the equivalent of energy or power consumption of running a light bulb. And ChatGPT, you know, we're all aware of it, is actually using the same amount of electricity as 33,000 US homes. So this is critically unsustainable. But the trend is only set to continue. So there's a really good plot from OpenAI, which I'm showing here, which is illustrating the computing demands of AI over time. And so for a long time, the AI demands followed Moore's law. So the rate at which hardware could improve was increasing at the same rate that AI was improving. And so, you know, it was all okay. But in these recent times, we're seeing AI doubling, the AI resources required doubling every 3.4 months. So you're getting about a 10 times increase in demand every year. And existing hardware is just not able to keep up with that demand. We're having to run our AI in data centers and consume an enormous amount of energy. I think Google have just announced that they're building nuclear reactors onto the sides of their data centers to cope with that demand. So all of this is ultimately coming down to the fact that in a conventional computer, you have a separate memory and processing unit. And so every time you want to do some data processing, you have to shuttle data between these two units, and that costs energy. And actually, I think something about like 60% of your smartphone battery is used just shuttling data. So what neuromorphic computing aims to do is combine these two units, the memory and your processing, into one system and offload some AI type processing onto a kind of optimized system that has some brain-like dynamics. So there are many different flavors of neuromorphic computing, and we heard a little bit about the chip layouts. And so, you know, there's a lot of effort, especially from big players such as Intel and Google and that kind of thing, to redesign existing CMOS architectures. But in the kind of academic world, there's also this physics-based neuromorphic computing. So really rethinking and redesigning the actual computing hardware itself. So an example of this is these memristor systems. There's a lot of excellent work going on there. We have optical computing. We heard a little bit about that just now. But we also have magnetic-based computing. So there's excellent work going on in the group of Julie Grolier, looking at MTJ-based computing. And what I'm going to talk to you about is nanomagnetic array-based computing. So what is a nanomagnetic array? So they kind of look like this, what they look like on the left here. You have a bunch of nano-patterned magnetic elements. So they're, you know, around 600 nanometers long, 200 wide. And when you order them in an array, you get some interactions between the different elements, and that can produce some very interesting collective behavior. So people have been studying these things for a while, for things such as emergent phenomena, like complex dynamics, as well as for computation. And so just to dive a little bit deeper about why these might be good for neuromorphic computing, so you can store information in the state of a magnetic element. So you can have things in these kind of macrospin or uniform states. You can also have the magnetization in a vortex state. And because they're close together and they're magnetic, you get some coupling between those. So you can do some processing of your memory state, you know, directly in the array. And so what happens is when you pattern these things close together, these individual elements no longer respond individually, but they respond collectively. And so you get this collective in-memory computing. We design these things and we make these things lithographically, so you can really tune what your system looks like, the shape and the kind of arrangement of these magnets, and we can use that to control how well the computing does. And finally, these systems have resonant frequencies in the gigahertz range. So you can maybe imagine a scheme one day in the future where you could implement or integrate these devices into telecoms technology. So the dream of kind of maybe making these systems would be to implement something like a deep neural network, or maybe a spiking network or something like that. Whilst these software networks are incredibly powerful, they're actually very hard to physically implement. So in this neural network scheme, you have many different weights that you have to tune and reconfigure, and trying to map that onto a nanomagnetic array, for example, it's not an easy step. So what we did first is implemented a reservoir computing scheme. So in a reservoir computer, you still have a kind of network here with all these interconnections between various nodes, but you don't train any of the connections here. You initialize them randomly and they remain fixed. And the only thing that's being trained is this output layer. So this is very simple and cheap to do. And people have shown that these types of networks can be very good for time series processing. And so what I'm going to show you is how we took this kind of software scheme and replaced the software reservoir layer with our nanomagnetic device. So there are a number of requirements you need from your physical system. You need some kind of nonlinearity to kind of linearly separate a complex data set. You need some high dimensionality. So if you're giving an input into your system, it's got to generate a rich set of dynamics, and you've got to have a large number of outputs to help with your training. And finally, particularly for time series tasks, you want this history-dependent response, or known in the field as a fading memory. So the output of your system at a particular time not only depends on its current input, but also on previous inputs. And so what I'm going to show you now is how we managed to engineer this fading memory into our samples. So just to maybe go a little bit into the physics now, just to kind of give you a feel for what's going on. We have a picture, a scanning electron microscope image of our device on the top left. And we've engineered some of the bars such that they can be bistable in a vortex or a macrospin state. So they can, they can exist in either of these states and at the same energy. And what we see is that if we apply magnetic fields to the sample to switch our elements, we see, and you can these are real magnetic images of what the magnetization texture is looking like. You see these little kind of things that look like defects here, and these are actually the vortices popping in. And we see that as we keep applying magnetic fields over and over again, the same input, we're getting a gradual nucleation of these vortex states. And on the bottom here, I'm also showing the resonance spectra. So going back to that kind of gigahertz resonance I was talking about, and we can see that we can, as these vortices are nucleated into our sample, we're seeing a strong change in our dynamics, which we can detect. We can track how these state populations are changing over time. We see that they exponentially decay or increase. And so, we're starting to get a sense of the nonlinearity coming into our samples. Also, if we're switching from vortices back to macrospins, we get a nonlinear response. And we also find that the dynamics of these kind of states evolving really depends on its history. So what we've done in this right plot here is we've started our sample in a number of different magnetic states, so a different percentage of macrospins and vortices. And that's what the different curves represent. And then what we did is we applied the same input to all of these different states and watched how the state populations evolved. So we started off with a strong input, which caused this spike in the response. And then we started with a lower input, which caused the states to decay again. And we see that the rate of the decay on this exponential curve really depends on the initial state that the system was in. So we're seeing that we've got this kind of history-dependent response. We've got some nonlinearity arising. And now the question is, okay, how can we implement some computing? So in order to kind of get a reasonable computing scheme, you need a way of reading data out. And for a while, people were looking at these systems and thinking, okay, we need to know what the state, the magnetization state of every element in our array is in order to get the computational readout. But these images that I'm showing you, they take about 30 minutes. So, you can't use this as a computer. It's going to take you, it's just not possible. So what we did in our group is we decided to have a closer look at this resonant readout that I was talking about, and found that if you can probe the dynamics of your system, you can actually infer a lot of information about what's going on in the state without having to kind of take the full picture. And so you can have we can have a look at how this resonant response evolves. Here I'm inputting a sine wave into our system, and we're seeing at the bottom here the kind of dynamics evolving over time, and so we can use that as a readout for our state. And then there's a question, okay, you've got your data, you've input your time series that you want to, you've got your data out. How do we then convert that into a computational result? How do we get it to do some computing? And so it's actually a really simple step. We just use linear regression. So we'll take our data set like this, we'll split it into a train and a test data set. And then with that training data set, the goal is to fit a set of weights using ridge regression or linear regression or something along those lines. We're going to fit a weight to every one of these frequency values. And then if all goes well, we should have something that looks like this, where you have a target in black and you have a prediction from the array that's based on your experimental data in red. So just to kind of summarize that a little bit, we're inputting our data via magnetic fields. We're measuring the the resonant response of the array as a readout, and then we're doing a simple, cheap software step to get the computational result. So now I'm going to go a bit into the computing and just to show you how these single arrays evolve. Here I've got 3 different samples. The kind of details aren't so important, but just so you're aware, we can really tune how these readouts look and the kind of non-linearities and the memories just by tuning our design of our samples. You can see these 3 different readouts are very different between these samples. And the first type of computing I'd like to show you is signal transformation tasks. So these are the tasks I'm going to show you are kind of benchmark tasks that maybe don't have so much real world applicability yet, but are really useful for kind of understanding what's going on. So the first is this signal transformation task. The goal here is you might input something like a sine wave, and you're going to transform that to a target such as a square wave or any kind of function that you want. So we've got our 3 arrays, and we can have a look at how they do at computing. So here's a particular target that we tried to transform it to. Here, the dotted red line is the target prediction. The prediction from the nanomagnets is in black, and then in blue, we show the prediction when you take the nanomagnets out of the computing pipeline. So really, all of the processing power is coming from the array itself and the array dynamics. And we see that different arrays perform differently, as you might expect. So we've got a very good array down here. But if we go to other tasks, such as this maybe slightly more complicated signal, we actually see that none of the arrays do very well. And this is actually a common theme in physical systems because your dynamics is hard-coded at the fabrication stage. The other types of tasks that we do are future prediction tasks. So here there's an equation called the Mackey-Class equation. It was originally developed to model blood hormone levels. So you could imagine, you might have some wearable health device that is monitoring your signals, and the goal here is to predict future values of that time series. And we can have a look at how the computational error changes as we try and predict into the future. And so this is the 3 different error curves for the 3 different samples I showed you. And what you see is that, again, for some tasks, we find that the arrays predict very well. But for other future steps, the arrays don't predict well at all. And you might have spotted, actually, the arrays are doing better at predicting 11 steps into the future than they're doing at predicting 7 steps into the future. But that doesn't make much sense. If you're predicting the weather, it should be the other way around. It should be harder to predict longer into the future. So that's coming from the kind of crazy periodicity of the input signal, but it's also a sign that our systems aren't really doing computing that well. So the question is, can we improve? Can we take our samples and can we build something that can improve on this? So what we know is that our system is a recurrent system. It has some history-dependent response. It's very nonlinear and it's high-dimensional. And so we can start to go back to our big neural network picture and start to think, okay, maybe we can actually use these different samples as nodes like you would in a neural network. So the first scheme we've tried was this kind of parallel input scheme. The goal here is you input your data into two different samples in parallel, and then you combine their output when you're doing the learning phase. And what we see is that when you do that, actually your performance gets a lot better. So here for this particular task, we got about a 5 times improvement in performance. But when we're trying to do the future prediction tasks, we don't see the same level of improvement. And that's because those tasks require a strong history dependence, and there's no way to improve the history dependence in this scheme. So we thought, okay, well, rather than putting them in parallel, let's try these series architectures where you take the input, you give it to one sample, you then take the output of that sample and feed it in as input to the next sample and have a look at the results. And we also created these kind of larger analogous physical neural network type things where you're kind of really starting to create these more complex networks where you have many different samples and many different interconnections. And so we can have a look at how this does at the prediction task again. And so here in the black is the best single array, and the other curves represent different series networks. And what we see is that the MSE is really flattened, the computational error is really flattened, and we're starting to do some proper, future prediction now. We can have a look at animations. Hopefully these come across okay. In the top, we have a single array. Again, the target is in red and the prediction from the array is in black. You can see that the single array doesn't do too well. It's noisy, it's not really following the curve that well. Whereas for the physical neural network architecture, we're really getting very, very high accuracy. Now, that's all good. But one of the kind of promising things about neuromorphic systems is that you're able to train on your device. And maybe one of the use cases in particular for if you're in an environment where there's changing conditions, maybe linking this to the underwater robots, is that you might face a scenario where maybe your sensor breaks or there's a changing task that you want to do and you want to be able to rapidly adapt to that change in environment.
Yes. So we're gonna wait until the technical team. Yes. Okay, we're trying to solve the theme. So at the moment, we're going to use this time only to remember you that tomorrow we will have another meeting. This bag, this wonderful bag, you don't need to bring it back with you. It's only a bag with something to write on. But this thing, it's useful for you, okay? Because it will help you get inside the building faster. So I recommend you, and especially the people who are coming here as assistants, to bring it. Second, remember that this morning we did some visits to the facilities, okay? Our original idea, sorry, I'm starting to be tired, was to visit the facilities now at the ending of this conference, but it's a bit late, and the facilities are better to be visited with light because they're full of windows and the sun goes inside the windows. And at night, it's more similar to a zombie apocalypse place than to the typical scientific research place you will love to visit. So that's why we're going to try and do the visits tomorrow, okay? I will tell you in the morning how you can sign up for this activity. Have we solved the problem with Killian, or we cannot solve the problem with Killian? Okay. Okay. So, free time. Get your mobile phones, speak with each other. Okay, Killian, can you hear us?
Hey, I can hear you.
Sorry, we lost you for 5 minutes more or less, but we're with you again. So I'm going to ask everyone to get seat and please let Killian finish. Actually, after your speech, I will be receiving questions for Killian. So think of it. And if any person has a question online, as we did it before, I will read it and Killian will listen to it. Thank you, Killian. You can continue.
Great, no worries. So I was just at this idea of if you've got a neuromorphic system, or okay, if you're in an application where you want to do some computing in a remote location, you might encounter a situation where there's a changing environment or changing conditions, perhaps a sensor breaks that you want to adapt to, perhaps the task that you want to do is slightly changed, and you want your system to be able to rapidly adapt to that changing task. So the goal that we tried to do is implement this idea of few-shot learning. So the goal here is that you set up your physical neural network in a way that it can rapidly adapt to these tasks. And we implemented 2 schemes. The first, the first is this rapid adaptability scheme. So we showed this the system just 50 data points of a new task that it hadn't seen before, and it was able to rapidly learn the dynamics of that equation and predict the future time steps. And we also tried this sparse data scheme. So we showed the system just 8 training points from this complex equation, and in just a few number of updates to the system's weights, it was able to adapt and learn this task. And just to show you, if we try that in a single array, it completely fails. So really, it's coming from the power of this kind of new physical neural network architecture. So far, I've shown you that the single arrays are kind of limited by their internal dynamics. But when you create these physical neural networks, you can enhance the performance and do things like few-shot learning. Now, that initial scheme was quite limited. We didn't do any training of the interconnections. So there's a question of, okay, can we create a trainable neural network? So the goal is this. We'll have maybe 3 different samples. They're all interconnected. You can arbitrarily choose these and you can train these interconnections. And in order to do that, we decided that we had to make a software analog. So the idea here is that we're going to make a software version of our network where we can train the neural network and then transfer the learned weights onto the device. So we have to know how the system responds to the current input and the current state. So like I was saying, the goal is to train what's known as a digital twin, where we would gather a bunch of experimental data, really use AI to learn the dynamics of our system in order to produce a software model. And I won't go into the details too much about how this works, only just to say that the model we developed very, very accurately matched the experiments. And it's really important that the software model does match the experiments very well, because otherwise when you transfer the weights from your software onto your hardware, it's going to, any differences in expected outputs are going to rapidly destroy the computational power. So here we have the experimental data and the model data. They overlap very nicely. So the goal here, okay, we're going to create this kind of neural network architecture, learn how to do a particular task in software, transfer the learned weights into the hardware, and then use that to test performance. And we've done a few different tasks. One of them is this sequential MNIST task, essentially a video classification task, where when we create a 2-layer neural network, we're able to get very low error percentages of about 3%. And we also implemented a neuroprosthetic gesture recognition task. So we got data from electrodes that are placed on your arm, and as you maybe clench your fist or wave your hand, the signals that the sensors read are slightly different. And so we input those signals into our device and trained it to classify what the gesture was. So what you can imagine is in the future is if you were to have a prosthetic arm, you could you could use these devices to convert electrical signals that come from your arm into the kind of prosthetic arm to mimic your hand action. And we also implemented a scheme called cascade learning. I won't go into the details of that, but we can do these regression tasks and these future prediction tasks very well to very high accuracy. So just to conclude, I'll wrap it up there. That I've kind of showed you that nanomagnetic systems are promising for the time series prediction, and that the physical neural networks enable this enhanced performance and this few-shot learning, and that we use a digital twin to train the physical neural networks. And currently, we're really working on miniaturizing our systems into devices. We've got some schemes in process to really drive down the energy consumption and increase the throughput of our devices. And then once we've done that, we'll be able to integrate those into kind of state-of-the-art devices such as these underwater robots or these neuroprosthetic things. Cool. Thank you very much.
Thank you very much, Killian. Is there any question in the room? Hands up. Hands up for questions for Killian. Anyone? Okay. So, Killian, I'm really sorry, but I'm not a technical expert, so I have no questions for you. I thought the other chairs might, but I don't. So, thank you very much for your explanation, for your speech, for your presentation. And
thanks.
This is the last topic, the last presentation for the day. I no need to say anything more because I think every piece of knowledge that has been shared here has an intrinsic value, and I hope that some of these ideas are important for you and help you get new ideas or help you start thinking that you should speak with some of the speakers or with someone in the public. Tomorrow we have another session, so for today, good night, and for tomorrow, I will welcome you to the Twilight Conference. Thank you very much.